Our observable universe is vast, yet it may only represent a fraction of what truly exists. Beyond the limits of our cosmic vision, who knows what mysteries lie waiting? Join us as we venture beyond the familiar, searching for answers to one of the greatest questions in science. What truly exists beyond the edge of the observable universe? Cosmic inflation, a theory born from the need to explain the early expansion of the universe, provides a fascinating insight into what may lie beyond. Just moments after the Big Bang, the universe underwent an incredibly rapid expansion. This is what we call cosmic inflation. This brief yet powerful period lasted for a fraction of a second, but it reshaped the universe in ways we're only beginning to understand. During this time, the universe expanded at an exponential rate, stretching space itself and pushing regions of it far beyond the reach of our telescopes. This swift expansion smoothed out any irregularities, making the universe appear nearly uniform in its vastness. But this leads us to an even more profound thought. If cosmic inflation pushed parts of space beyond our observable horizon, could there be vast areas of the universe that remain hidden from us? What if entire regions of space harbor completely different physical properties, or even different laws of physics? Could this mean that our universe is just one bubble among countless others, each one existing with its unique characteristics? This thought leads us to the mind-bending idea of a multiverse, where the observable universe we know is only one of many bubbles, each with its own distinct physical realities. Moreover, cosmic inflation has even deeper implications. It suggests that the very structures we see today, galaxies, clusters of galaxies, and the intricate web of matter throughout the universe, were seeded during this brief moment of rapid inflation. The fluctuations in energy density during inflation led to the formation of these large-scale structures, guiding matter to gather under gravity's influence over billions of years. So the galaxies and clusters that we observe today, they might have begun their journey during that brief moment of cosmic inflation. The concept of regions beyond our observable universe challenges our understanding of reality, sparking deeper questions about the very nature of the cosmos. If inflation truly took place, it opens the door to fascinating possibilities about what might exist just beyond the reach of our sight. This concept isn't just theoretical, it also introduces us to a mind-expanding idea called eternal inflation. Building on the foundation of cosmic inflation, eternal inflation posits that inflationary processes don't occur just once, but can happen repeatedly across different regions of space and time. This leads to the hypothesis that the universe is constantly inflating in some areas, creating an infinite number of universes, each with its own conditions and physical laws. Picture it. The universe is like a vast sea of inflating space, with individual universes appearing as bubbles within it. Each bubble represents a distinct universe, and within each, different sets of physical phenomena could unfold. Some bubbles might lead to universes with different dimensions or altered constants of nature, giving rise to a cosmically diverse multiverse. What's truly remarkable about eternal inflation is how it reconciles the idea of a single Big Bang with the diversity we see in the universe. Rather than just one singular event, eternal inflation suggests a never-ending timeline of Big Bang-like events, each giving birth to a new universe. Each of these universes can have entirely different characteristics, from the fundamental constants of physics to the laws that govern them. This means that, while we might perceive ourselves as the sole inhabitants of one universe, we are actually part of a far larger multiverse, where countless variations of existence unfold in parallel. Eternal inflation stretches the limits of our conventional understanding, suggesting that the universe we observe is just a tiny fragment of a far grander and more complex cosmic landscape. In this view, our universe is not the only one that exists. Rather, it's just one of an infinite number of universes that have arisen from the process of ongoing cosmic inflation. Each of these universes could be vastly different, yet all share the same origin in the initial inflationary event. Inflation theory doesn't stop here. There are different models of inflation that offer alternative visions of how inflation occurs, two prominent ones being slow-roll inflation and chaotic inflation. Slow-roll inflation describes a gradual, extended period of inflation where a scalar field slowly descends down its potential energy curve, leading to a more controlled and uniform expansion. This kind of inflation creates a universe that can support regions with varying properties, yet those regions share fundamental underlying characteristics. In the slow roll model, the gradual nature of inflation allows distinct pocket universes or bubbles to form. These bubbles could have different physical properties, resulting in universes that operate under completely different rules of nature. But despite these differences, each bubble universe would still share an observable connection to the larger inflationary event that spawned them. In essence, these models, slow roll inflation, chaotic inflation, and eternal inflation, present a universe far more vast and diverse than we ever imagined. The observable universe we know, stretching across vast galaxies and clusters of stars, may just be a small, isolated corner of a much larger multiverse, where the possibilities for different kinds of universes are limitless. As we continue to push the boundaries of our cosmic understanding, we find ourselves contemplating the nature of infinity itself, pondering whether our universe is truly unique or just one of many, each one birthed by an ongoing process of cosmic inflation. The future of cosmology may reveal a universe teeming with endless variations, all linked by the mysterious process of inflation that shapes the very fabric of spacetime. Chaotic inflation, on the other hand, presents a fascinating and far more unpredictable view of the cosmos. It emerges when we consider the influence of highly energetic fields and initial conditions that are not uniform across the universe. In this model, inflation is triggered by significant divergences in energy levels across different regions of space. Unlike more structured models of inflation, chaotic inflation introduces the possibility of a multiverse where nearly any set of initial conditions could lead to inflation. This gives rise to an incredibly vast and diverse range of universes, each one potentially unique in its properties, laws, and behaviors. The diversity within this model is staggering. With energy scales fluctuating wildly, it's possible for universes to arise where the physical constants differ dramatically from our own. These universes could be inhospitable or might function under entirely different rules than we are accustomed to. Imagine a universe where gravity behaves differently, or where the forces of nature are arranged in a way we can't even comprehend. The implications of chaotic inflation are profound, as it paints a picture of a multiverse that is far from homogeneous. Instead of a shared set of laws governing all universes, each one could operate under its own set of rules, creating a collection of realms that are drastically distinct from each other. This concept raises profound questions about the very fabric of reality. What does it mean for something to be real when so many different versions of reality could exist? If the constants of nature can vary across different universes, what does this imply about the nature of life itself? What conditions foster the emergence of life in such a boundless and diverse cosmos? These questions challenge our understanding of existence at the deepest level, forcing us to reconsider what we know about the universe and our place within it. Central to the theory of inflationary cosmology is the concept of bubble nucleation. This process describes how distinct regions of space undergo phase transitions during the rapid inflationary expansion. As inflation pushes space to expand at an unprecedented rate, it causes different areas of the cosmos to split off and undergo their own independent developments. These newly separated regions, or bubbles, emerge with their own set of physical properties, creating new universes that may have entirely different laws governing them. The process of bubble nucleation is sparked when the inflationary field begins to lose energy. This loss of energy triggers a local event, causing a phase transition in certain regions. As this transition occurs, it gives birth to a bubble, which expands rapidly, creating a new domain where the physical laws may diverge from those in the surrounding space. Within these bubbles, the laws of physics can vary, giving birth to new universes with potentially completely different constants and conditions. This process is essentially the birth of a new universe every time a bubble forms. The potential for multiple bubble nucleations across the cosmos means that countless bubbles can form, each one representing a different outcome, a different set of physical laws, and perhaps a completely different universe. These bubbles are not just one-off events, but could happen continually across an infinite expanse of space. Each bubble is a unique world with its own set of circumstances evolving independently from all others. As inflation continues, these bubbles emerge at a staggering pace, each with its own possibilities unfolding in real time. In this way, the universe we know might not be the only one that exists. Instead, it could be just one of countless bubbles within a vast, overarching multiverse. As each bubble grows and evolves, it could harbor its own unique conditions and properties, making the multiverse a truly infinite landscape of diverse and potentially unimaginable realms. The idea of bubble nucleation not only enriches our understanding of the origins of our own universe, but also opens up fascinating discussions about the nature of reality itself. Could our entire existence be just one of an infinite number of possible outcomes, each shaped by its own conditions, rules, and possibilities? This intricate process adds a layer of complexity to our understanding of the cosmos, pushing the boundaries of science, philosophy, and existential inquiry. The reality of a multiverse full of diverse, self-contained universes challenges us to think in ways that defy conventional logic, inviting us to explore the deeper truths of existence in an ever-expanding cosmic playground. In this vast cosmos, where the very fabric of existence pulses with infinite potential, we encounter a mind-boggling possibility. What if multiple universes exist, each sprouting from the same foundational principles yet diverging into an astonishing variety of forms? The concept that the cosmos could be teeming with universes is not just science fiction, but a serious theoretical framework in modern cosmology. This notion is rooted in inflationary theory, which posits that the early universe underwent a rapid expansion, seeding the conditions for countless distinct pocket universes to emerge. These pocket universes formed during the inflationary phase of the universe. Inflation, a concept involving the exponential growth of space-time in the first moments after the Big Bang, causes different regions of space to inflate at different rates. This uneven expansion creates zones where the energy field responsible for inflation fluctuates, eventually causing these regions to freeze and stop inflating. These regions, now independent of the rest, become distinct pocket universes, each with unique properties and physical laws. Picture this like boiling water. As bubbles form, each one becomes its own separate entity. Similarly, each pocket universe behaves as its own universe, expanding and evolving with its own set of physical constants, laws, and possibly dimensions. These universes, though originating from the same inflationary event, may share similar properties, or they could evolve in ways that are radically different from anything we could imagine. Some may even have conditions entirely hostile to life, while others might have environments not too dissimilar to our own. The implications of this theory are profound, as it suggests that the universe is not a singular, homogeneous entity, but rather a complex network of interlinked universes, each one born from the same fundamental process of inflation. This leads to a crucial question. What truly defines a universe? Are we the only pocket universe in existence, or are we merely one among an infinite number of others, each with its own rules and possibilities? Such an idea shifts our understanding of reality and challenges our perceptions of what the cosmos could be. The very notion of a multiverse, multiple universes within the same overarching inflationary space, forces us to rethink our place in the vast, uncharted expanse of the cosmos. If every pocket universe evolves differently, then the sheer variety of cosmic structures could be staggering. Some universes could harbor forms of life and intelligence, while others might be so alien in their physical properties that life as we know it would be impossible. Inflationary cosmology does more than just introduce the concept of pocket universes. It also solves some of the most puzzling issues in cosmology, like the horizon and flatness problems. The horizon problem points to the observation that distant regions of the universe, despite being separated by vast distances, have nearly identical temperatures and properties. Without inflation, it's hard to see how these regions could have exchanged energy or information, since light hasn't had enough time to travel between them since the Big Bang. Inflation solves this by proposing that these regions were once much closer before the rapid expansion, thus allowing them to share similar characteristics despite their present separation. The flatness problem, another conundrum in cosmology, questions why our universe appears to be so close to a critical density, neither open nor closed. Theoretically, any deviation from this ideal balance should have grown over time, leading to a universe that would either expand indefinitely or collapse upon itself. However, inflation smooths out the early universe, driving it toward a nearly perfect flatness, explaining the observed uniformity we see today. Together, these ideas not only answer some of the universe's deepest mysteries, but also pave the way for the possibility of an infinite array of cosmic scenarios. The notion that multiple universes might exist, each formed under different circumstances, provides an awe-inspiring framework for understanding the vastness of the cosmos. It forces us to reconsider everything we thought we knew about space, time, and the very nature of existence. The possibility of countless pocket universes, each evolving according to its own rules, opens up an extraordinary realm of cosmic possibilities just waiting to be explored. However, the observable geometry of the universe is surprisingly flat. Given the vast span of time since the Big Bang, this seems improbable, yet inflationary theory offers a resolution. It proposes that a dramatic expansion in the early universe stretched any initial curvature so immensely that it rendered the cosmos nearly perfectly flat, thereby diluting any spatial curvature that may have existed earlier. This inflationary model opens the door to a thrilling possibility. The nature of space beyond our observable universe could be vastly different, stretching far beyond our current comprehension. If inflation continues to occur in certain regions, it suggests that our universe is far from the finite realm we perceive. In fact, it could be endlessly sprawling, giving rise to an infinite number of bubble universes that exist beyond our observational limits. These bubbles would be distinct regions of space, each with its own physical laws and constants. This ever-expanding landscape could imply that our universe is just one bubble in a vast multiverse, each universe forming and evolving along unique evolutionary trajectories. These new bubbles could be entirely out of our reach, potentially containing realities with properties we cannot yet imagine, reshaping our understanding of the cosmos and the very nature of existence itself. At the heart of this theory is the concept of false vacuum decay, a process that suggests our universe might currently exist in a metastable state, referred to as a false vacuum. In this context, a vacuum isn't empty space, but a state of minimal energy. However, a false vacuum isn't the lowest possible energy state for the universe. Instead, it represents a local minimum where conditions seem stable but are not truly secure. If the universe undergoes a transition from this false vacuum to a true vacuum state, it could experience dramatic shifts in the fabric of space-time. These changes could give birth to entirely new universes. The process of false vacuum decay might occur through quantum tunneling, a quantum phenomenon that allows the system to escape from the false vacuum state and fall into a more stable, true vacuum. This tunneling creates a bubble of true vacuum that expands at an exponential rate. As this bubble grows, it forms a new universe, distinct from the previous one. This idea echoes the principles of inflationary cosmology, in which inflation stretches space to the point of creating new pockets of space-time that evolve independently. These bubbles could possess unique physical properties, different constants, and even entirely distinct laws of physics, shaping new realities in ways unimaginable. In this way, false vacuum decay serves as a potential driver for the birth of an entire multiverse. Each bubble universe born from this decay could follow its own path of evolution, leading to outcomes as diverse as the constants and physical laws that define each one. The implications of this theory are immense, not just for our understanding of how new universes form, but for the future of our own cosmos. Some theorists have even speculated that our universe may already be undergoing this process of decay. If true, this raises profound questions about the stability of our universe and its ultimate fate. The concept of the inflationary multiverse presents a distinct framework within the broader multiverse theory. It differs significantly from other ideas about parallel universes, particularly in its mechanisms and the way it explains the emergence of multiple universes. In the inflationary multiverse, the rapid expansion of space during inflation leads to fluctuations in the inflationary field, which in turn gives birth to isolated pocket universes, each with its own set of physical laws and constants. These bubbles emerge from a shared inflationary state, meaning that every new universe begins from the same fundamental process of inflation. This framework stands apart from models such as the quantum multiverse, which arises from the many worlds interpretation of quantum mechanics. The quantum multiverse suggests that every quantum decision spawns a branching reality, leading to an infinite number of possibilities. While both theories suggest the existence of parallel universes, the inflationary multiverse offers a clearer, more structured model for how these universes might arise and what they might look like. Moreover, the inflationary multiverse offers a solution to one of the most perplexing problems in cosmology, the fine-tuning problem. While other multiverse theories propose that our universe is just one of many randomly generated outcomes, the inflationary multiverse suggests that the properties of different universes are a direct consequence of inflationary processes. Regions of space can stop inflating at different times, creating distinct bubbles with tailored properties based on their initial conditions. This idea provides a more comprehensive framework for understanding how diverse physical laws and constants could emerge in different universes, solving some of the puzzles that other multiverse models cannot address. In the end, the theory of the inflationary multiverse opens up new possibilities for the nature of reality itself, offering a glimpse into an ever-expanding cosmos full of infinite potential. Whether or not our universe is part of this grand multiversal structure, the idea there could be other realms beyond our reach compels us to reconsider the fundamental nature of space, time, and existence. The question of whether we are merely one bubble in an endless cosmic sea is one that may never be fully answered, but it drives us to look further, deeper, and more inquisitively into the mysteries of the universe. The multiverse is a concept that stretches the boundaries of imagination, offering us a glimpse into the vast expanse of reality beyond what we can see. While many theories of the multiverse are grounded in abstract ideas like string theory or speculative cosmological models, the inflationary multiverse presents a compelling, observation-backed argument. Unlike those theories that delve into hypothetical dimensions or alternate laws of physics, the inflationary multiverse is grounded in the real-world evidence we've gathered from phenomena like the cosmic microwave background radiation. This makes it a particularly powerful and scientifically rigorous concept, one that paints a picture of an infinite number of realities that stretch beyond our observable universe, all while staying rooted in the principles of cosmic inflation. At the core of this theory is the idea of cosmic inflation, an incredibly rapid expansion that took place just moments after the Big Bang. This expansion helps explain many of the perplexing features of the universe we observe today, especially the uniformity of the cosmic microwave background radiation. This radiation is a remnant from the very early universe, a faint afterglow that fills the cosmos, acting as a snapshot of the infant universe in its formative stages. Observations from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have revealed that this radiation is strikingly uniform across vast regions of the sky. This is a puzzle, as regions of space that are incredibly far apart should have had no way of interacting or exchanging information before inflation. According to the theory, the rapid expansion of the universe stretched these regions so that they could form homogeneously before becoming causally disconnected from one another. This idea leads to an intriguing implication, that inflation didn't just happen in the observable universe. It might have continued in regions that lie beyond our cosmic horizon, creating realms we cannot yet see. This extends the notion of the universe beyond our reach, presenting the possibility that the true scale of the cosmos is much larger than what we can currently measure. Evidence for this comes from the minute temperature fluctuations in the cosmic microwave background radiation, variations that reveal density differences that eventually grew into galaxies and other large-scale structures. These fluctuations are thought to be quantum perturbations, stretched and magnified during the inflationary phase. The theory suggests that these fluctuations could also occur in regions beyond our sight, leading to further inflationary events and the creation of new cosmic structures in the distant reaches of space. Another avenue for supporting the idea of an eternally inflating universe lies in the study of gravitational waves. These ripples in spacetime, generated by cataclysmic events like the collision of black holes or neutron stars, have the potential to provide crucial insights into the ongoing effects of inflation. Future experiments, like those from the LIGO and Virgo observatories, may detect gravitational waves originating from inflationary processes that happened long before the formation of stars and galaxies. Specifically, the unique spectrum of gravitational waves produced by inflationary interactions could serve as a signature of this epochal event, offering a direct link between the distant past of our universe and the observable phenomena we witness today. This observational evidence forms a powerful case for the idea that cosmic inflation, this incredibly rapid expansion, continues to shape the universe in ways we are just beginning to comprehend. These findings not only support the theory of inflation, but also hint at the possibility that inflation is still at work, creating an ever-expanding universe that extends far beyond our sight. It raises fascinating questions about the nature of reality itself, and invites us to consider the potential existence of an infinite cosmos that awaits discovery. At the heart of this theory lies the idea of eternal inflation, which suggests that inflationary processes don't occur uniformly across the entire universe. Instead, certain regions may continue to inflate indefinitely, giving rise to new bubble universes within the larger fabric of the cosmos. This leads to a fractal-like structure of the multiverse, where the process of inflation repeats at different scales. Just as a fractal pattern repeats itself infinitely, creating intricate self-similar designs, the universe could be structured in a way where large bubbles of space contain smaller ones, each undergoing its own inflationary events. The result is a self-perpetuating landscape, constantly evolving and expanding in a manner reminiscent of the recursive patterns found in fractals. The implications of this fractal-like structure are profound. As we explore the bubble universes within this vast multiverse, we find that each one has its own unique characteristics. Some may stabilize into regions where life, galaxies, and stars can form, while others may remain in an inflationary state, constantly generating new bubbles. This diversity presents an endlessly varied cosmic landscape where the larger structures, like galaxies and clusters of galaxies, are just one layer in an infinitely repeating pattern of creation. In a fractal universe, the larger picture is reflected in the smaller scales, with each bubble universe containing the potential for further inflationary processes, giving rise to even more cosmic structures. This fractal-like arrangement is more than a mere metaphor. It's a literal description of the multiverse, suggesting that the universe we observe is only a small part of an infinitely complex self-similar system. It challenges us to rethink the nature of existence, pushing us to explore not just the farthest reaches of our observable universe, but also the possibility of endless forms of reality, each existing in its own unique inflationary pocket. This framework of eternal inflation invites us to consider the vastness and intricacy of the cosmos, offering a compelling picture of a universe, or perhaps many universes, that are interconnected by the same fundamental dynamics of cosmic inflation. Through this lens, the cosmos transforms from a static entity into a dynamic, ever-evolving network of realities, each shaped by the ongoing processes of inflation. It's a model that challenges us to broaden our understanding of reality itself and opens the door to infinite possibilities, each waiting to be explored as we venture further into the mysteries of the universe. In the complex and captivating realm of cosmology, the concept of the multiverse stretches the boundaries of our understanding, beckoning us to explore realms beyond our comprehension. Central to this grand exploration is string theory, a framework that suggests the existence of countless universes, each one unique, tied together by a profound connection, the vibrations of tiny, one-dimensional strings. These strings, unlike traditional point-like particles, vibrate in different modes, with each mode giving rise to the myriad particles and forces we encounter in our reality. The theory proposes that what we perceive as the familiar four dimensions, three of space and one of time, are just the surface, a mere shadow of a vast and largely hidden multiverse, potentially teeming with diverse and extraordinary realities. At the heart of string theory is the notion of extra dimensions, dimensions that extend beyond the observable universe and are hidden from our perception. These dimensions, while imperceptible, can manifest in various configurations, curving or compactifying in intricate patterns that shape the very laws of physics in each universe. This landscape of possible dimension leads to the idea of a multiverse, where each configuration of extra dimensions gives birth to a different universe, governed by its own set of physical laws. Within this infinite landscape, our universe is but one of many possible outcomes, shaped by the particular vibrational states of strings and the specific compactification of its extra dimensions. String theory's vast possibilities are most apparent when considering the theory's multiple solutions, particularly regarding the configurations of extra dimensions. These dimensions can be compactified in an infinite variety of ways, creating a landscape of possibilities so vast that it defies imagination. As a result, string theory doesn't just suggest the existence of parallel universes. It offers a comprehensive framework to understand how these universes could emerge and evolve. Each distinct universe in the multiverse may exhibit different physical constants, properties, and behaviors, determined by the specific vibrational state of its strings and the way its extra dimensions are compactified. This creates a vast, potentially infinite tapestry of universes, each with its own unique characteristics, some of which may even harbor life, while others remain inhospitable. The intriguing aspect of this theory is how these multiple universes could be born. String theory provides a variety of mechanisms for universe creation, including ideas akin to cosmic inflation. In some scenarios, regions of space may experience inflation differently, giving rise to distinct bubble or pocket universes. Each of these universes could undergo its own version of inflation, shaping its structure and properties based on the specific vibrational states of its strings and the compactification of its extra dimensions. These pocket universes could be completely different from one another, governed by distinct physical laws and constants, opening up the possibility of entirely unique realities, some even with radically different dimensions of space and time. Beyond these awe-inspiring possibilities, string theory invites us to question the very nature of reality. If the theory is correct, our universe may be just one of many, each existing within a grand, interconnected cosmic framework. The infinite array of potential universes challenges our traditional notions of a singular, self-contained existence. It suggests that the universe we inhabit, with its finely tuned laws and constants, may be just one lucky outcome among a multitude of possibilities. Perhaps we are here not because our universe was specially chosen, but because the conditions that support life happen to emerge from the vast array of configurations in this cosmic landscape. The concept of the string theory landscape provides not only a theoretical framework, but a way to visualize the grand architecture of the multiverse. This landscape consists of a vast number of possible solutions, each corresponding to a distinct universe with different laws of physics and constants. These solutions arise from the process of compactification, where extra dimensions curl up into complex shapes, each shaping the behavior of the universe in a unique way. Some configurations may produce universes that are similar to our own, while others may lead to entirely different laws of physics that creating entirely new and unimaginable realities. This landscape of possibilities also sheds light on the concept of vacuum states, distinct, stable configurations of the universe that correspond to different physical laws. Each vacuum state represents a possible universe with its own set of constants, energies, and physical behaviors. The process of transitioning between different vacuum states could give rise to the formation of new universes, akin to the process of eternal inflation, where bubbles of space-time expand and evolve independently, creating a multitude of distinct pocket universes. This mechanism not only explains the vast diversity of possible universes, but also addresses some of the deepest questions in cosmology, such as why our universe appears so finely tuned for life. In a multiverse of countless configurations, the universe we inhabit may simply be one of the many that happen to have the conditions necessary for life, with many others potentially being inhospitable. The implications of string theory stretch far beyond just the question of existence. They challenge our very understanding of reality, offering a tantalizing glimpse into a universe or many universes that are far more complex, interconnected, and strange than we could have ever imagined. As we continue to explore this theory, the potential for uncovering new dimensions of reality seems boundless, propelling us toward a future where the mysteries of the multiverse could finally be within our reach. In this fascinating realm of string theory, we are led to contemplate some of the most profound and enigmatic questions about the very fabric of reality itself. What if the universe we know is just one small part of an unimaginable multiverse? How do the mechanisms that govern our existence relate to the fundamental laws that could define other, entirely separate universes? As we dive into the intricate nature of string theory, the idea of extra dimensions emerges as a crucial element in this cosmic puzzle. While we are accustomed to experiencing reality through the lens of 3 dimensions of space and 1 dimension of time, string theory challenges this view by proposing that there are additional spatial dimensions beyond our direct perception. These extra dimensions, typically compactified or hidden from our sensory grasp, have the potential to influence the physical properties of everything we observe, from the smallest particles to the grandest cosmic structures. They might even harbor other universes within them, each with its own unique set of physical laws and constants. Imagine a scenario where extra dimensions serve as gateways to distinct realities, created through the concept of compactification. In string theory, these dimensions can be folded or compacted in different ways, giving rise to varying physical properties that govern each universe. One configuration might lead to a universe strikingly similar to ours, while another could produce entirely different laws of nature. The possibilities are virtually endless. Each compactification scheme could correspond to a completely separate universe, one with distinct characteristics, forces, and interactions. This creates a rich landscape of universes side by side, each with its own unique rules governing its very existence. These extra dimensions don't just create different realities, they also provide a means for universes to interact with one another. Within this multiverse framework, the extra dimensions might act as conduits, linking separate vacuum states, distinct configurations of energy and particle physics. Some regions of these hidden dimensions could stabilize into separate vacua, each evolving into its own universe. These vacua may not only remain isolated, but could interact through complex processes, enabling transitions between states or even the birth of entirely new universes through events similar to bubble nucleation. It's a profound thought. Universes can emerge from each other, growing from the very same fundamental principles that govern the multiverse. Further complicating this cosmic web, these extra dimensions could also allow for the complete isolation of universes from one another. While originating from the same string-theoretic foundation, universes might evolve independently with their own set of physical laws. The geometry of each extra-dimensional configuration could shape the fundamental properties of the universe it governs, allowing for an immense diversity of possibilities. This creates a multiverse where each universe coexists with countless others, each one potentially capable of harboring life or not, depending on the particular physical rules it follows. As we delve deeper into the multiverse, it becomes clear that the inclusion of extra dimensions in string theory isn't just an abstract concept. It invites us to rethink the very essence of existence. The varied configurations of extra dimensions pose fundamental questions about the nature of reality itself. How do these hidden realms influence the observed universe? Could they offer a glimpse into the underlying structure of all that we know and all that we have yet to discover? One particularly captivating idea within this framework is brain cosmology, which introduces the notion of multidimensional objects known as brains, short for membranes. In this context, our universe can be envisioned as a 3-dimensional brain embedded within a higher dimensional space called the bulk. The bulk contains not just our universe, but other brains and dimensions, each with its own unique characteristics. The interactions between these brains could lead to the creation of new universes, with events such as collisions between brains potentially triggering phenomena like the Big Bang. This concept radically reshapes our understanding of the universe. Instead of viewing our reality as isolated, brain cosmology suggests that it could be part of a much larger and more complex multidimensional landscape. Each brain could host its own universe with its own set of physical laws. These laws may be similar to ours or radically different, depending on the specific properties of the brain on which each universe resides. Thus, the multiverse is not simply a collection of parallel universes, but a dynamic and evolving network of interconnected realities, each one shaped by the interaction of higher dimensional objects. The implications of brain cosmology are far-reaching. Not only does it offer a framework for understanding the existence of parallel universes, but it also challenges our traditional notions of space and time. The interactions between these higher dimensional brains could have profound effects on the evolution of our own universe, influencing its structure, its laws, and even its future. It prompts us to ask fundamental questions. How did our universe come to be? What is the true nature of reality? How are we connected to the vast, multidimensional landscape of the multiverse? In this extraordinary view of the cosmos, we find ourselves confronted with the possibility that the universe we inhabit may not be the only one. Instead, it could be just one of many brains floating within a higher dimensional bulk. The dynamics of these brains may govern the formation and evolution of universes in ways we have yet to fully comprehend. As we continue to explore the mysteries of string theory and brain cosmology, we are invited to consider the infinite complexities of existence and the profound connections between the universes that might exist alongside our own. The journey to understanding the multiverse is just beginning, and the questions it raises promise to redefine our understanding of the cosmos and our place within it. In the vastness of our understanding of the universe, brain cosmology lays the foundation for a profound, interconnected web of universes. These universes are intricately woven together within a higher dimensional framework, each contributing its own unique thread to the grand fabric of existence. At the heart of this intricate structure lies M-theory, a revolutionary framework in theoretical physics. Its primary ambition is to unify the 5 distinct string theories that have emerged over the years, each one describing fundamental particles as one-dimensional strings. But these theories diverge, differing in the number of dimensions they inhabit and the types of strings they incorporate. M-theory takes an audacious step forward by introducing the 11th dimension, a critical key to connecting these divergent theories. By bringing them together, M-theory suggests that what we perceive as different string theories are simply various manifestations of the same underlying principles. This unified structure serves as the foundation of M-theory, offering a grander and more cohesive vision of the cosmos. A crucial breakthrough of M-theory is its description of higher dimensional objects known as brains. While traditional string theories are focused on one-dimensional strings, brains can exist as two-dimensional surfaces or even higher dimensional structures. This introduction of complex multidimensionality provides a more expansive lens to understand the universe, opening the door to phenomena that were previously beyond the reach of conventional string theories. The 11th dimension proves essential in this framework, adding a richness and versatility that paints a more intricate picture of space-time than we could have imagined. But the implications of M-theory go far beyond simply unifying various string theories. One of the most mind-bending aspects of M-theory is its connection to the idea of the multiverse. The multiverse suggests that our universe might not be the only one. It may be just one of many, each with its own set of physical laws and constants. With the additional dimensions and the dynamics of brain interactions, M-theory paints a picture of a landscape where countless universes could emerge, each with its own configuration of strings and brains. This opens up the tantalizing possibility of multiple realities, each shaped by the unique topological properties of their higher dimensional constructs. As scientists dive deeper into the intricacies of M-theory, they uncover connections to phenomena that have long baffled cosmologists. From the mysteries of cosmic inflation to the nature of black holes, M-theory helps us begin to understand how the universe operates at the most fundamental levels. What was once the realm of abstract speculation is now gaining traction, drawing together various theoretical concepts and offering a tantalizing glimpse into the complexity of the cosmos. The multiverse, once a purely speculative idea, may now become a cornerstone of our understanding of the physical world. Parallel to M theory, the erotic model offers a captivating alternative perspective on the origins of our universe. According to this model, the universe we know emerged from the collision of two three-dimensional brains within a higher dimensional space. This collision takes place in a landscape that includes extra dimensions, which are central to the model's mechanics. Unlike the Big Bang theory, which suggests a singular explosive event originating from an infinitely dense point, the erotic model posits that the universe began as a result of two distinct brains coming together. In this model, the brains represent separate universes. When they collide, the friction and energy generated by the interaction can produce a hot, dense state that mirrors the conditions of the Big Bang. This collision sparks processes similar to those described by cosmic inflation, propelling the newly formed universe into a period of rapid expansion. The inclusion of extra dimensions in this model allows for a more nuanced and comprehensive understanding of cosmological phenomena, providing an elegant explanation for various features of the universe that the traditional Big Bang theory struggles to account for. One of the critical advantages of the erotic model is its ability to address some of the most significant challenges faced by conventional cosmology. For example, the issue of homogeneity and isotropy in the universe, why matter and energy appear evenly distributed across vast distances, can be resolved by the extra-dimensional framework. In this model, the complexity of higher dimensional space allows for a more diverse set of initial conditions, giving rise to a wide range of possible outcomes. The interaction of brains offers a natural explanation for the uniform distribution of matter and energy, as well as the variations seen in the cosmic microwave background radiation. Furthermore, the erotic model introduces the concept of the multiverse in a novel way. If our universe is the result of a brain collision, it raises the possibility that other brains exist, each potentially giving birth to its own universe with different physical properties. This raises profound questions about the very nature of reality and opens the door to a deeper exploration of the cosmos. As researchers continue to explore this extra-dimensional framework, the erotic model offers a fresh and innovative approach to understanding the origin of our universe. In this universe, the collision of brains becomes a pivotal event in the erotic model of cosmology. Here, the brains are visualized as distinct universes, each residing on a three-dimensional surface within a higher dimensional space. As these brains move through the fabric of this higher dimensional space, their interaction can lead to dramatic and far-reaching consequences. When two brains collide, the energy released can compress the fabric of space-time, triggering a state of extreme density and temperature. This intense interaction generates a series of dynamic processes that resemble the conditions described by traditional Big Bang cosmology. As the energy from the collision bursts into existence, it may give rise to particles and radiation, effectively forming a new cosmos that begins to expand. The resulting universe follows an inflationary phase, smoothing out any irregularities and creating the uniform structure observed in the cosmos today. This expansion explains the vastness of space and the uniform distribution of the cosmic microwave background radiation, shedding light on some of the most fundamental questions about the universe's origins and structure. In essence, the collision of brains offers a remarkable and innovative mechanism for the creation of new universes. As we explore these interactions in greater depth, we are faced with a profound realization. The universe we live in may not be the only one. Instead, it could be one of many, each birthed through its own extraordinary process. Moreover, imagine a reality where the very fabric of the universe is in a constant dance, an intricate ballet of higher dimensional space. In this remarkable scenario, every collision of cosmic brains could birth an entirely new universe. Each collision would carry its own distinct characteristics, shaped by the conditions that prevailed during that momentous event. Picture this as a cyclical process, one that hints at a vast and endless multiverse, a cosmic web of universes, each with its own set of physical laws, making it a part of the ever-expanding tapestry of reality. The idea that our universe may have arisen from such brain collisions invites us to take a step back and re-examine the fundamental nature of existence. What if these collisions are not isolated phenomena, but rather an ongoing sequence of events, an interconnected chain in a grand cosmic symphony? The very notion of our universe being a product of this kind of interaction stirs a deeper philosophical inquiry into the unseen dimensions that could be woven into the very core of everything we observe. Could there be realms beyond the dimensions we can perceive, and are we truly grasping the full extent of reality? In the realm of theoretical physics, the holographic principle emerges as a captivating concept that challenges our traditional views on space and dimensions. This principle suggests that all the information contained within a volume of space could, in theory, be encoded on its boundary, much like a hologram, where a two-dimensional image can represent a three-dimensional object. This bold idea suggests that what we perceive as a three-dimensional universe may, in fact, be a projection of more fundamental two-dimensional information. Originally rooted in black hole thermodynamics, where it was discovered that the entropy of a black hole is proportional to the area of its event horizon rather than its volume, the holographic principle extends far beyond the confines of black holes. It presents a profound shift in how we understand the nature of space, time, and the laws of physics. Imagine a universe where what we experience as three-dimensional space is simply an illusion, a projection of a more intricate reality encoded on a two-dimensional surface. This perspective would fundamentally reshape our understanding of gravity, quantum mechanics, and thermodynamics, inviting new approaches to explore how these forces interact on both the cosmic and quantum scales. When considering universes beyond our own, the holographic principle suggests an even more mind-boggling possibility. Each universe may exist as a unique holographic projection created from the specific information encoded on its own boundary. This aligns with the multiverse theory, where an infinite array of parallel realities could emerge, each governed by its own set of physical rules. Just as each point on a hologram carries information about the whole, these different universes could each possess distinct properties, all connected in ways we may not yet understand. This intriguing possibility hints at the unification of quantum mechanics and gravity, offering a glimpse of a deeper connection between our universe and others that may exist within a vast, interconnected cosmic landscape. In the realm of string theory, the idea of compactified dimensions provides another key piece of the puzzle in understanding the universe's deeper structure. String theory proposes that the basic building blocks of the universe are not point-like particles, but rather one-dimensional strings that vibrate at various frequencies. To explain the behavior of these strings as we observe them in our three-dimensional world, string theory suggests that extraspatial dimensions must exist. However, these extra dimensions aren't immediately observable. They are compactified, meaning they are curled up into tiny, hidden shapes, often at scales far beyond the reach of our current experimental tools. The concept of compactified dimensions could be the key to linking the phenomena we experience on a daily basis with the far more mysterious realms of the extra dimensions. These dimensions could potentially offer insights into how different universes within the vast multiverse interact with one another, or how they might be constructed from the same underlying strings. Such a discovery would not only reshape our understanding of the physical world, but could also lead us closer to unlocking the fundamental truths of reality itself. In this ever-evolving landscape of cosmic discovery, these theories are more than just abstract ideas. They represent the frontier of human understanding, guiding us toward new ways of thinking about the universe, its origins, and its infinite possibilities. Every breakthrough brings us one step closer to unraveling the mysteries that lie hidden just beyond our perception. As we look deeper into the fabric of the cosmos, we may discover that the boundary between our universe and others is not as fixed as we once thought, and that the dimensions we perceive may be only a fraction of the vast, interconnected whole. In this universe, we are accustomed to experiencing 3 dimensions of space. But what if there were more? While our everyday reality is shaped by these familiar dimensions, theories like string theory suggest that there could be 6 or even more hidden dimensions, compactified in ways we can't directly observe. These additional dimensions may have geometries that are vastly different from anything we can comprehend. The properties of these compactified dimensions could have profound effects on the very nature of the strings that underpin the particles as we see in our universe. The arrangement of these hidden dimensions might play a pivotal role in determining not just the structure of our universe, but also the potential for other universes to exist. Each specific way that these dimensions are compactified could give rise to a completely different universe, governed by its own unique set of physical laws, constants, and fundamental forces. This leads to the intriguing idea of a multiverse, where numerous universes coexist, each shaped by a different configuration of compact dimensions. As scientists continue to explore the implications of these compactified dimensions, they encounter the fascinating possibility that our universe may be just one of many, emerging from a higher dimensional framework. Each arrangement of the compact dimensions would create a universe with distinct physical rules and properties, offering new insights into the very nature of existence. This exploration touches on the broader landscape of cosmology, where the connection between string theory and the structure of the universe offers us a glimpse into a reality far beyond our own. The notion of extra dimensions is a fundamental aspect of string theory, as well as other advanced theories in modern physics. However, these extra dimensions remain elusive, and direct observational evidence has proven difficult to obtain. Nevertheless, scientists are exploring several experimental approaches that might give us indirect evidence of their existence. One promising avenue is the study of gravity at extremely small scales. Some theoretical models predict that if extra dimensions exist, gravity could behave differently than it does in the familiar three-dimensional world, particularly at distances much smaller than those we currently probe. Experiments designed to measure the inverse square law of gravity at tiny distances might reveal subtle deviations from what we expect based on the laws of gravity in our three-dimensional space. If gravity were to weaken more rapidly at small scales, this could suggest the presence of extra dimensions that influence the gravitational force in ways we cannot directly perceive. High-energy particle physics also offers a potential path to uncovering evidence for extra dimensions. Particle accelerators, such as the Large Hadron Collider, LHC, could provide crucial insights. In certain models inspired by string theory, collisions at extremely high energies could produce particles that escape into extra dimensions. This would lead to missing energy or unexpected momentum patterns in the data, offering tantalizing clues about the presence of hidden dimensions. Additionally, these extra dimensions could give rise to unique particles like Kaluza-Klein modes, which are manifestations of higher dimensional physics. Detecting these particles could provide another piece of the puzzle. Beyond the realm of particle physics, cosmic phenomena may also offer a window into the existence of extra dimensions. For example, the behavior of cosmic rays, which travel through space at ultra-high energies, could be influenced by unseen dimensions. Studying how these cosmic rays interact with the fabric of space-time could help us detect the subtle effects of extra dimensions, offering an indirect but compelling signature of their existence. As our understanding of the universe continues to evolve, these hidden dimensions could reveal much more than just the structure of our own reality. They could open up entire new realms of existence, where different laws of physics govern the behavior of matter and energy. The search for extra dimensions is not just a quest to understand the nature of our universe, but a journey that could lead us to discover entirely new forms of reality. In the vast expanse of the universe, gravitational waves, ripples in space-time caused by massive objects, hold the potential to unravel the deepest mysteries of the cosmos. These waves, first predicted by Albert Einstein, are like cosmic messengers carrying crucial information about the objects that produce them. If extra dimensions exist beyond our familiar three-dimensional world, they may leave a fingerprint on the propagation of these waves. Such an insight could revolutionize our understanding of the universe's structure, shedding light on whether space-time itself is more intricate than we've imagined. Gravitational waves could help us probe the very fabric of reality. Extra dimensions, hypothesized in string theory, could alter how waves move across the cosmos. By carefully studying these waves, scientists might discern the nature of these dimensions, how many there are, and how they interact with our familiar three-dimensional world. This research may offer clues about the fundamental forces that shape everything, from the tiniest particles to the vastest galaxies. As we peer deeper into the universe, the ripple effects of these waves may reveal a more complex reality than we ever thought possible. Furthermore, observations related to cosmic inflation, the rapid expansion of the universe just after the Big Bang, hint at a connection to higher dimensional physics. Some inflationary models propose the existence of these extra dimensions, with profound implications for our understanding of the universe's creation. If these dimensions are real, they could influence the very nature of the early universe. One way to uncover this is by analyzing the cosmic microwave background radiation, the faint afterglow of the Big Bang, looking for signatures that may indicate the presence of hidden dimensions. The discovery of such features would provide compelling evidence, confirming that the universe is more than just the three-dimensional reality we perceive. These multi-layered scientific endeavors represent the tireless effort to decipher the universe's deepest secrets. With each discovery, we move closer to understanding not only the forces that govern the cosmos, but also our place within it. The potential revelation of extra dimensions would forever alter our view of reality, opening doors to entirely new realms of physics and philosophy. Turning to quantum mechanics, the many worlds interpretation offers a radical shift in how we understand quantum events. This theory, still controversial among physicists, suggests that rather than collapsing into one reality when a quantum event occurs, the universe splits into multiple branches, each realizing one possible outcome. Imagine a quantum event with multiple potential outcomes. Each one doesn't collapse into a singular reality, as suggested by the Copenhagen interpretation. Instead, every outcome exists simultaneously in parallel universes. This is a bold and elegant solution to the paradox of quantum mechanics, which suggests that all possibilities happen in separate, non-communicating branches of reality. The many worlds interpretation is rooted in the mathematical framework of quantum mechanics, where particles exist in multiple states until measured. In this view, measurement doesn't cause the collapse of the quantum wave function, as traditionally believed. Instead, it triggers the branching of the universe, creating parallel realities. For instance, if an event can happen in two ways, both realities occur in separate universes, and each observer only experiences one of them. The infinite number of universes that arise from every quantum event forms a vast multiverse, where every choice and random event spawns a new reality. The implications of this interpretation are profound. If each decision and chance event creates a new universe, it invites speculation about how our lives could have unfolded differently in alternate realities. It raises questions about the nature of identity and the role of choice in shaping our existence. While the many worlds interpretation provides a consistent and elegant framework for understanding quantum mechanics, it lacks empirical predictions that can be tested. This is a significant critique, yet it continues to intrigue and inspire physicists who are captivated by its philosophical and conceptual richness. Central to this interpretation is quantum decoherence, a process that helps explain why parallel universes don't interfere with one another. Decoherence occurs when a quantum system interacts with its environment, causing the superposition of states to collapse into distinct outcomes. In the context of the many worlds theory, decoherence ensures that different quantum events don't interfere with each other, allowing each universe to branch into a separate, independent reality. This provides a solid foundation for why we perceive only one outcome in our reality, even though all possibilities exist in parallel. As quantum systems lose their coherence through interactions with their environment, the potential outcomes of quantum events become independent of each other. This means that while the universe may have initially been in a superposition of possibilities, decoherence causes these possibilities to manifest as distinct realities. This process not only underpins the many worlds interpretation, but also explains why macroscopic objects, despite being composed of quantum particles, seem to follow classical laws of physics. The constant interaction with their surroundings helps them behave in ways that appear deterministic, bridging the gap between the strange world of quantum mechanics and the familiar classical reality. Quantum tunneling is another phenomenon that reveals the fascinating oddities of the quantum world. It describes the ability of particles to pass through energy barriers, even when classical physics says they don't have enough energy. Imagine a ball rolling towards a hill. If it doesn't have enough energy, it should roll back. But in the quantum world, particles can tunnel through the barrier, appearing on the other side without having the classical energy needed to overcome it. This mysterious ability is a direct result of the wave-like nature of particles and highlights the unpredictability of the quantum realm. In this universe, particles behave in ways that challenge our intuition and understanding of the world around us. While classical physics would predict one outcome, quantum mechanics opens up a world of strange possibilities, where particles can exist in multiple places at once, or even tunnel through barriers. These behaviors push the boundaries of what we know and force us to rethink the very nature of reality. As science progresses, the intersection of gravitational waves, quantum mechanics, and the possibility of hidden dimensions may provide the answers we need to understand not only the origins of the universe, but the deeper fabric of existence itself. However, in the quantum realm, particles are not merely points moving through space, but rather exist as wave functions, a mathematical representation of probabilities. This means that instead of being confined to a specific location, a particle's position is defined by a range of possibilities, all with varying degrees of likelihood. One of the most intriguing phenomena arising from this wave-like behavior is quantum tunneling, where particles can tunnel through barriers that, in classical physics, would be insurmountable. When a particle encounters a barrier, whether it's a physical wall or an energy threshold, it doesn't simply stop at the edge. Instead, its wave function stretches into and beyond the barrier, reflecting the probability that the particle might appear on the other side. While the likelihood of the particle's successful tunneling decreases with the barrier's height or thickness, it never completely vanishes. This finite probability persists, offering a fascinating challenge to our classical understanding of physics. Quantum tunneling isn't just a theoretical curiosity. It has profound real-world implications, especially in areas like nuclear fusion. In the core of stars, for instance, protons, positively charged particles, should repel each other due to their like charges. Yet, quantum tunneling allows them to get close enough to overcome this repulsion, enabling nuclear fusion. This mechanism is the key to the energy production of stars, including our sun. But the implications of quantum tunneling stretch far beyond the stars. In cosmology, it's theorized that quantum tunneling could be responsible for the birth of new universes. Imagine a region of space existing in a metastable state, known as a false vacuum. This state is not the most stable configuration for the energy of the system, but it's stuck in a local minimum, unable to transition to a true vacuum. Quantum tunneling provides a potential route for this transition, allowing the universe to escape from its current state and undergo rapid inflationary expansion, an event that could give rise to the formation of an entirely new universe. This process ties directly into the multiverse theory, which suggests that our universe might be just one of countless others, each with its own set of physical constants and properties. Quantum tunneling could be the mechanism that allows these different universes to form. As each tunneling event occurs, it might create a new branch of reality, leading to the emergence of a new universe, distinct from the ones before it. These universes, while governed by the same quantum principles, could manifest under entirely different conditions, giving rise to a diversity of outcomes and possibilities across the multiverse. In essence, quantum tunneling offers not only an extraordinary glimpse into the bizarre behavior of particles, but also a potential key to understanding the origins of the cosmos. Whether explaining the energy processes that power stars or offering a theoretical mechanism for the birth of new universes, tunneling serves as both a captivating scientific insight and a conceptual tool that may help unlock the mysteries of the universe itself. In the realms of quantum mechanics and cosmology, a captivating interplay unfolds that challenges our most fundamental understanding of existence, reality, and the vast cosmos. This profound connection has the potential to reshape our view of the universe itself. The Copenhagen interpretation and the many worlds interpretation, two of the most influential views in quantum theory, offer radically different perspectives on the nature of reality. Each stems from unique assumptions about quantum mechanics, with implications that extend far beyond the realm of physics. The Copenhagen interpretation, often regarded as one of the earliest and most traditional approaches, suggests that quantum systems do not have fixed properties until they are observed or measured. According to this interpretation, particles exist in a state of superposition, where they can simultaneously occupy multiple states until the moment of measurement. When an observation is made, the wave function collapses, resolving the system into a single definitive outcome, which is what the observer perceives. However, the many worlds interpretation presents a strikingly different viewpoint. Rather than accepting the collapse of the wave function upon observation, this theory suggests that every possible outcome of a quantum event occurs, but each in a separate, non-communicating branch of the universe. This interpretation posits that all possible realities coexist simultaneously in a vast multiversal expanse, with every possible state being realized in a different universe. Crucially, the many worlds theory eliminates the need for an observer to collapse the wave function. In this model, quantum systems evolve coherently throughout the measurement process, maintaining their wave-like nature. This fundamental difference between the two interpretations leads to drastically different views on the nature of reality itself. The Copenhagen interpretation introduces an element of randomness into quantum mechanics. The act of observation, by determining which outcome is realized, creates an inherent unpredictability. It raises questions about the role of consciousness and the act of measurement in shaping the reality we experience. In this view, there is a single universe defined by the outcomes of measurements performed by observers. Only one outcome is realized at any given moment. On the other hand, the many worlds interpretation removes randomness from the equation entirely. It suggests that reality is deterministic, with all possible outcomes unfolding within a branching multiverse. Each observer experiences only one branch of this multiverse, which accounts for the apparent randomness observed in quantum mechanics. However, in this view, all possible outcomes are realized, albeit in parallel universes. The many worlds interpretation provides a unified framework that eliminates the need for wave function collapse, offering a more comprehensive and elegant understanding of quantum behavior. In this interpretation, the role of the observer is reconceptualized, and the multiverse theory presents a richer, more expansive model of reality. The philosophical implications of these divergent perspectives are profound. While the Copenhagen interpretation underscores the critical role of measurement in shaping the reality we perceive, the many worlds interpretation offers a more expansive view, where every possibility is realized across a multitude of coexisting universes. This shift in perspective not only alters our understanding of the physical universe, but also invites deeper contemplation of existence, consciousness, and the nature of the cosmos itself. At the heart of these discussions lies quantum entanglement, a fundamental phenomenon that has puzzled scientists and philosophers alike. Entanglement occurs when two or more particles become interconnected in such a way that the state of one particle instantaneously influences the state of the other, regardless of the distance between them. When two particles are entangled, measuring the state of one particle instantly provides information about the state of its entangled counterpart. This connection persists even if the particles are separated by vast distances, a phenomenon famously referred to by Albert Einstein as spooky action at a distance. In the context of multiple universes, entanglement plays a critical role in the many worlds interpretation of quantum mechanics. According to this theory, each quantum event with multiple potential outcomes causes the universe to branch into separate realities, each representing a different outcome. When particles are entangled, the measurement of one particle's state does not collapse the system into a single outcome. Instead, it reflects the outcome of the entire entangled state, which manifests across all branches of the multiverse. What makes entanglement particularly fascinating in the context of the multiverse is the interconnectedness it implies between different branches of reality. When a measurement occurs in one universe, resulting in a specific outcome, It influences the states of the entangled particles across all other universes. This creates a form of correlation between parallel realities, even though these universes operate independently of one another. The entangled nature of particles suggests a potential relationship between separate branches of the multiverse, even though they appear to be completely distinct. As we continue to explore the mysteries of quantum mechanics and cosmology, the implications of these theories challenge not only our understanding of the physical universe, but also the very nature of reality itself. Both the Copenhagen and many worlds interpretations offer rich insights into the fundamental workings of the cosmos, yet they leave us with profound questions about existence, consciousness, and the endless possibilities that lie beyond our comprehension. Quantum entanglement has long captured the imagination of scientists and philosophers alike, raising profound questions about the nature of reality, information, and the very structure of the cosmos. As researchers continue to explore its mysteries, they uncover startling implications that stretch far beyond the conventional boundaries of physics. At its core, quantum entanglement suggests that particles, no matter how far apart they are, remain mysteriously connected, with their states intertwined. This entanglement isn't just a physical phenomenon, but hints at the existence of multiple branching universes, each containing information about the states of entangled particles. The idea that these universes might share overlapping historic data creates an astonishing tapestry of interrelated realities that could redefine our understanding of both quantum mechanics and the fabric of existence itself. Entangled particles can be seen as the conduits that link these multiple universes, providing a direct connection through their shared quantum properties. This means that every observation or interaction with a quantum system may, in fact, be a step towards understanding not just one reality, but countless others. As the quantum world and the concept of parallel universes collide, it becomes apparent that the very structure of reality is far more complex than previously thought. Quantum entanglement is more than a peculiar occurrence. It is a doorway to understanding the deep interconnectedness of the universe at its most fundamental level. Moreover, quantum superposition, another cornerstone of quantum mechanics, plays a crucial role in this understanding. Superposition states that a quantum system can exist in multiple states at once, until it is observed. This paradoxical concept, which allows particles to be in multiple positions or states simultaneously, directly challenges our classical understanding of reality. The wave function, which mathematically represents all possible outcomes, is only collapsed into a definite state when observed. Prior to this collapse, the particle embodies every potential outcome. In the context of the many worlds interpretation of quantum mechanics, the role of superposition takes on a new level of significance. Rather than collapsing into one specific state upon observation, the wave function continues to evolve, creating new branches of reality. Each possible outcome of an experiment, whether a particle spins up or down, results in the universe splitting into distinct branches, each corresponding to one of the possible outcomes. In this view, superposition becomes the mechanism through which an endless number of realities are created, each one stemming from a different quantum possibility. For example, consider a quantum experiment where a particle exists in a state of spin up or spin down. In superposition, the particle is both spin up and spin down simultaneously. Upon measurement, instead of collapsing into one definitive state, the universe branches. One reality reflects the particle's spin up state, while another reveals its spin down state. This dual reality highlights the key role that superposition plays in the creation of multiple parallel universes, universes that exist simultaneously, each representing a different outcome of a quantum event. This branching process is a striking reflection of the vast multiverse that may exist, with each branch representing an entirely different version of reality. As quantum processes unfold, they give rise to new worlds, each evolving from different quantum decisions and outcomes. The many worlds interpretation thus intricately ties quantum superposition to the creation of these parallel realities, suggesting that the very act of quantum measurement leads to the proliferation of universes, each with its own set of possibilities and experiences. The idea of parallel universes is both fascinating and daunting, as it forces us to reconsider the nature of reality itself. If each quantum event results in the creation of a new universe, the number of possible realities becomes virtually infinite. Each of these universes evolves independently, yet they are all interconnected through the underlying principles of quantum mechanics. This view of reality suggests that the universe we observe may be only one of countless others, each with its own unique history and future, all stemming from the same fundamental quantum processes. In addition to these groundbreaking ideas, the role of observation in quantum mechanics further complicates our understanding of reality. The traditional Copenhagen interpretation proposes that the state of a quantum system exists in superposition until it is measured. Only upon observation does the system collapse into a definite state. This raises critical questions about the observer's role in shaping reality. Is the observer simply a passive entity, or does their consciousness play an active part in the collapse of the wave function? The measurement problem, which explores how and why wave function collapse occurs, remains one of the most intriguing challenges in quantum mechanics. The implications of this concept go beyond our universe. If consciousness can influence the outcome of quantum measurements, could the same principles apply in parallel universes or other dimensions? Could observers in these other realms also play a role in shaping the realities they experience? If each universe is governed by the same quantum laws, it stands to reason that each one may interact with its observers in distinct ways. The result could be a multitude of universes, each shaped by the consciousness of its inhabitants and the unique quantum interactions they partake in. As our understanding of quantum mechanics deepens, it becomes increasingly clear that the universe is far more intricate and interconnected than we ever imagined. From quantum entanglement to superposition, from parallel universes to the profound role of observation, these concepts challenge everything we think we know about reality. They invite us to look beyond the visible universe and consider a vast multiverse, where every quantum decision creates a new reality, and where the observer is an active participant in shaping the outcome of existence itself. As we continue to explore these mysteries, we move ever closer to understanding the true nature of reality, one that may stretch far beyond the confines of our imagination. In exploring the complexities of quantum mechanics, the notion of observation becomes far more than a mere act of witnessing. Rather than collapsing the wave function into a single deterministic outcome, the many worlds interpretation suggests that observation triggers the branching of multiple universes. Each branch represents a different outcome, giving rise to countless parallel realities. In this view, reality isn't singular, it's the coexistence of infinite possibilities. Observation doesn't shape our universe into one defined existence. Instead, it differentiates the experiences of observers across a vast multiverse. The role of observation thus challenges traditional understandings, offering a new lens through which to examine not only our own universe, but also the endless web of interconnected realities that may exist beyond our perception. The question now extends beyond whether there is one reality, but how we as observers experience and relate to an infinite number of potential worlds. The implications of this understanding extend into the core of quantum mechanics, inviting us to reconsider what we perceive as real. Whether we accept the classic interpretation where observation collapses probabilities or explore the multiverse framework, these ideas push the boundaries of what we believe about existence. Our understanding of the cosmos, our universe in its vast complexity, is no longer just a single story. It is a potential tapestry of countless stories, each unfolding simultaneously in countless alternate worlds. Moving from the philosophical to the scientific, quantum foam theory provides another intriguing glimpse into the nature of reality, describing a chaotic, fluctuating landscape at the smallest scales of space-time, specifically at the Planck scale. Proposed by renowned physicist John Wheeler, quantum foam suggests that at these incredibly minuscule dimensions, space-time is anything but smooth and continuous. Instead, it behaves like a frothy, turbulent sea, with quantum fluctuations giving rise to virtual particles that appear and disappear in an ever-changing dance. This dynamic, unpredictable nature of the universe at the most fundamental level redefines the structure of space-time, showing it as an unstable and fluid reality rather than the static, continuous fabric we experience in our everyday lives. Yet quantum foam doesn't stop at describing the unstable nature of space-time. It also offers a fascinating potential mechanism for the creation of new universes. These small fluctuations in the foam can lead to the formation of baby universes, distinct, self-contained universes that branch off from our own. This process involves a localized region within the foam where quantum fluctuations trigger a rapid expansion, much like the inflationary period believed to have occurred in the early moments of our own universe. These mini-universes could develop their own unique laws of physics and evolve independently, creating entirely new cosmic realms. Far from being a theoretical fantasy, this idea merges seamlessly with the multiverse theory, suggesting that our universe may not be the only one. Instead, a vast interconnected web of universes could exist, all with their own distinct realities. Each fluctuation in the quantum foam could give birth to new realities, each of which could expand and evolve in ways we might never fully understand. Intriguingly, this theory also ties into the concept of wormholes, hypothetical bridges through space-time that connect distant regions of the universe. If these bridges exist, they could link different universes within the multiverse, providing a potential means of travel or connection between parallel realms. Such a notion offers profound implications for our understanding of space and time, suggesting that the quantum foam could be the very medium facilitating the existence and interconnection of multiple universes. In this context, a baby universe isn't just a cosmic curiosity. It represents the possibility of an entirely new, self-contained reality, potentially governed by its own laws of physics. If it stabilizes, it could grow and evolve independently, perhaps even expanding forever, just as our own universe is believed to do. The quantum foam could in fact be the cradle of new cosmos, endlessly birthing new worlds within the broader multiverse. This interplay of quantum mechanics and cosmology leads us to quantum cosmology, a field at the intersection of quantum theory and the study of the universe's origins. By applying quantum principles to cosmological phenomena, researchers seek to understand the very fabric of space-time, as well as the conditions that led to the birth and evolution of the universe. This groundbreaking field offers the possibility of answering age-old questions. How did the universe begin? How did space and time evolve? What is the ultimate nature of existence? As we venture into these deeper realms of understanding, we uncover a more intricate, complex structure of reality than ever before imagined. Quantum mechanics, with its strange and often bewildering principles, doesn't just explain the microcosm of particles and waves. It opens a window into the vastness of the universe, suggesting that the cosmos may not be as we perceive it. It is a realm of infinite potential, a quantum landscape teeming with possibilities that challenge everything we think we know about existence. In conclusion, the theories of quantum foam, parallel universes, and the many worlds interpretation don't merely describe abstract scientific concepts. They offer a radically different way of understanding the universe, the nature of reality, and our place within it. As science continues to probe the mysteries of the quantum world, we may one day uncover answers that redefine not just our understanding of the cosmos, but the very essence of existence itself. Quantum cosmology presents a revolutionary way of thinking about the universe, one that challenges everything we know about reality. At the heart of this mind-bending concept is the idea of the universe as a quantum object. Imagine the entire cosmos as a vast, complex wave function, a mathematical construct that holds within it all the possible states, configurations, and futures of the universe. Through this framework, the universe is no longer a singular static entity, but a dynamic, probabilistic construct, where every moment is alive with countless possibilities. This approach invites us to explore the scenarios where the classical understanding of the universe dissolves into quantum fluctuations, where multiple outcomes can coexist, each with its own trajectory. One of the central pillars of quantum cosmology is the consideration of quantum gravity, which aims to explain how gravity functions at the tiniest, most fundamental scales. By delving into quantum gravity, we gain deeper insights into the origins of the universe, especially the early moments when space and time themselves were in flux. Among the most intriguing aspects of quantum cosmology is its role in explaining the potential existence of multiple universes, a concept that has captivated both scientists and philosophers alike. At the center of this idea lies the theory of the multiverse, particularly within the framework of inflationary cosmology. During the inflationary epoch, a period immediately following the Big Bang, the universe is believed to have undergone a rapid exponential expansion. This process, powered by quantum fluctuations, could have led to regions of space-time expanding at different rates. Over time, these distinct regions could have developed into separate universes, each with unique physical laws and constants. In this scenario, our universe may not be the only one. It could be just one of many, all arising from a common quantum origin. Furthermore, quantum cosmology proposes the fascinating idea of quantum tunneling, an event that could spark the creation of new universes. In these models, high-energy regions of spacetime could tunnel through to lower energy states, forming what we could call baby universes. These nascent realms would evolve independently from our own, that are potentially governed by different laws of physics and distinct sets of fundamental constants. This idea further enriches the concept of the multiverse, suggesting that our universe might just be a small part of an immense, ever-growing cosmic tapestry. Each new universe, emerging from its own quantum event, would add complexity and variety to the cosmic landscape. As we dive deeper into quantum cosmology, we encounter one of its most intriguing aspects: quantum fluctuations. These fleeting, minuscule events occur as a direct consequence of the uncertainty principle, a fundamental aspect of quantum mechanics. This principle posits that certain pairs of physical properties, such as position and momentum, cannot be precisely measured simultaneously. In the empty void of space, where we would expect nothing to exist, quantum mechanics shows us that energy levels fluctuate, creating tiny, transient particles that appear and disappear in the blink of an eye. These quantum fluctuations may play a crucial role in the birth of new universes. In some cosmological models, fluctuations in energy can reach a critical threshold, triggering a process called inflation, which causes a tiny patch of space to undergo rapid expansion. This inflationary phase could be the catalyst for the creation of entirely new universes, each born from the quantum fluctuations of a pre-existing vacuum. The implications of these ideas are staggering. If quantum fluctuations can give rise to entire universes, then the concept of the multiverse becomes a plausible reality. Instead of being the sole universe, we might exist as just one of many, each universe having its own laws of physics, dimensions, and even fundamental constants. The quantum realm, where reality seems to defy the conventional rules of logic and time, becomes a breeding ground for countless variations of existence. In this view, our universe could simply be one bubble in an endless sea of universes, each with its own unique characteristics. This mind-expanding perspective challenges our traditional understanding of the cosmos. What we perceive as our singular universe could be just one of an infinite number of universes, all emerging from the same quantum fabric. The implications stretch far beyond science, touching on the deepest questions of philosophy, existence, and the very nature of reality. Could our universe be the product of a random quantum fluctuation? And if so, what does that say about the nature of existence itself? The quilted multiverse theory presents another breathtaking vision of reality. According to this theory, our universe is but one patch in an immense, ever-expanding quilt of universes. This idea emerges from the theory of cosmic inflation, which suggests that in the early moments following the Big Bang, space expanded at a phenomenally rapid rate. However, this expansion may not have been uniform, leading to regions of space that continued inflating long after others had stopped. These regions could give birth to entirely separate universes, each one developing independently and potentially possessing vastly different physical properties. The distances between these universes within the quilt would be so vast that they may be completely beyond our ability to observe or interact with. In some regions, universes might resemble our own, with similar laws of physics and dimensions, while in others, the differences could be so pronounced that the very nature of existence would be unrecognizable. Each universe within the quilt could have its own unique set of forces, particles, and physical constants, making the cosmic tapestry an awe-inspiring collection of infinite possibilities. In this model, the fabric of reality itself becomes a vast, interconnected structure, with each universe contributing to the whole. The multiverse, once a speculative idea, becomes a real dynamic framework, constantly evolving and expanding. As we push the boundaries of quantum cosmology, we find ourselves confronted with a radically new understanding of the cosmos, one that calls into question the very nature of existence. Perhaps we are not alone in this vast universe after all. Perhaps we are merely one thread in the grand, infinite fabric of the multiverse. In the vast expanse of the cosmos, the concept of the observable universe holds profound significance. We, as human beings, are confined to a small slice of the universe, what we can observe. The boundary of this observable universe is dictated by the speed of light and the finite age of the cosmos itself. Beyond this observable horizon, a realm of infinite possibilities may exist, encompassing untold numbers of other universes. Each universe could follow its own unique history, evolution, and structure, emerging from the same fundamental processes that shaped our own universe. This realization brings with it a humbling perspective on existence. What we perceive as reality is but a tiny fragment of the entire cosmic tapestry. The idea of a quilted multiverse offers a framework for understanding this grand design. It presents an image of the multiverse as a cosmic quilt, where each universe forms a distinct patch in an expansive and intricate whole. This theory invites deep philosophical inquiry into the very nature of existence. If an infinite number of universes exist, each with its own distinct set of laws, possibilities, and histories, it challenges us to rethink concepts such as fate, randomness, and even the nature of reality itself. Our universe, which we consider the entirety of existence, may just be one thread in a vast cosmic weave. And within this larger framework, each patch in the cosmic quilt plays its own crucial role, contributing to the multiverse's grand design. A fundamental concept in understanding the structure of the cosmos, as well as the possibility of multiple universes, is that of Hubble volumes. A Hubble volume refers to a region of space determined by the distance light travels over a set period, typically the age of the universe. This concept is essential for astronomers, helping them understand the distribution and behavior of matter and energy within the observable universe. A Hubble volume encapsulates a basic scale of the universe's structure, which assumes that space is uniform on the grandest scales, a principle known as the cosmological principle. However, the notion of Hubble volumes becomes even more fascinating when considering the possibility of multiple universes. If inflationary processes, the rapid expansion that occurred after the Big Bang, were not uniform, it could lead to different regions of space, each with its own set of physical laws. This leads to the exciting idea that a single Hubble volume could contain a vast array of distinct universes, each with its own physical conditions, development stages, and laws of nature. In essence, each Hubble volume could potentially be a universe in its own right, contributing to an even greater multiversal structure. Within this multiversal framework, our observable universe would be just one Hubble volume among many. The implications of this idea radically alter how we view the cosmos. No longer would we be confined to understanding our universe in isolation. Instead, we would be challenged to think beyond the limits of our own cosmos and imagine a broader cosmic architecture. The possibility of infinite universes, each with its own set of rules, suggests that the multiverse could contain an unimaginable variety of conditions and realities, each unique in its makeup. This perspective redefines the boundaries of reality itself, urging us to consider not just what we can observe, but also what lies beyond our understanding. A particularly intriguing theory in this context is that of Fion universes, proposed by the physicist Alexander Vilenkin. This unconventional idea posits that new universes could emerge through a process similar to biological reproduction, with one universe giving birth to another. It draws connections between cosmology and quantum physics, specifically focusing on inflation and the multiverse. According to the theory, certain regions of space, after undergoing rapid inflation, could create daughter universes through a process akin to biological budding. This expansion could trigger local instabilities, causing the formation of entirely new universes with distinct physical laws and constants. What makes this theory even more compelling is the notion that each daughter universe could operate under entirely different physical rules, dimensions, or constants, expanding the diversity of the multiverse exponentially. This gives rise to a potentially infinite sequence of universes, each capable of generating its own progeny. The idea that universes might create offspring universes allows for a deeper exploration of the nature of cosmic creation, highlighting the possibility that our universe, like any other, could be just one phase in an ongoing cycle of cosmic birth and rebirth. In many ways, the theory of Fion universes challenges our traditional understanding of creation. By looking at the birth of universes through the lens of reproduction, it introduces a radically new way of thinking about the origins of reality itself. It suggests that the cosmos may not be a singular, isolated event, but rather part of a much broader and more interconnected cycle of cosmic processes. This notion expands our comprehension of the universe, offering new insights into the fundamental forces that govern existence. It invites us to reflect not just on our own universe's origins, but on the interconnectedness of all the universes within the multiverse, raising questions about the very fabric of reality and the processes that sustain it. In conclusion, the study of the multiverse, from Hubble volumes to the theory of Fion universes, reveals a cosmos far more complex and awe-inspiring than we could have imagined. Each new discovery pushes the boundaries of our understanding, urging us to look beyond the horizon of our observable universe and consider a much larger, infinitely diverse cosmic structure. It challenges our deepest beliefs about existence and invites us to embrace the possibility that the universe we know is just a small piece of a grand, interconnected multiverse. The journey into this vast cosmic mystery is only just beginning. Lee Smolin's concept of cosmic natural selection presents an innovative way to understand the evolution of universes, blending the principles of biological evolution with the vastness of the cosmos. He proposes that universes, much like species in nature, go through a selection process. In this cosmic version of natural selection, a universe's properties and constants influence its ability to give rise to new universes. These new universes emerge from black holes, which act as the reproductive mechanisms of the cosmos. When a black hole forms in a universe, it can give birth to a new universe, one that might have different physical laws and constants, potentially optimizing its chances of survival in the cosmic landscape. This idea stems from the understanding that the more successful universes are those that can sustain processes like star formation over long periods, leading to the creation of black holes. These black holes, in turn, generate offspring universes. Over time, this creates a kind of cosmic evolution where the most fit universes, those that are more likely to form black holes, succeed in passing on their characteristics to new generations of universes. This process challenges traditional views that the constants of our universe are fixed. Instead, it opens the possibility that these constants are shaped by the historical lineage of previous universes, selected over time through the evolutionary pressures of cosmic natural selection. The implications of this theory are far-reaching. If Smolin's framework holds true, the fundamental constants of our universe, such as the strength of gravity or the speed of light, could be the results of evolutionary pressures that have been passed down through generations of universes. This would suggest that the universe is not a static entity, but rather a dynamic system influenced by the survival of the fittest universes. Furthermore, it raises profound questions about the interconnectedness of universes within the multiverse, highlighting the potential for cosmic adaptation through natural selection. Smolin's theory not only deepens our understanding of cosmic evolution, but also bridges the realms of physics and evolutionary biology, suggesting that the universe's very structure is shaped by the survival and propagation of successful cosmic entities. The idea that universes evolve over time, driven by processes similar to natural selection, creates a fascinating narrative for how the cosmos unfolds through time, with each universe representing an experiment in survival, adaptation, and reproduction. Max Tegmark, on the other hand, introduces an entirely different perspective on the nature of the universe with his mathematical universe hypothesis. This bold theory contends that reality, at its core, is entirely mathematical. According to Tegmark, every possible mathematical structure exists, and those that exhibit the right level of complexity manifest as physical realities. In this view, the universe we experience is merely one of an infinite number of potential universes, each defined by its own unique mathematical structure. This hypothesis radically alters our understanding of reality. Instead of seeing mathematics as a tool for describing the universe, Tegmark proposes that it is the fundamental fabric of existence itself. In this model, every conceivable mathematical form corresponds to an actual physical universe. These universes may have vastly different physical laws, constants, and dimensions, or they could operate in ways that are beyond our comprehension, universes where logic and causality work in unexpected and alien ways. By suggesting that all possible universes are mathematically real, Tegmark opens the door to a multiverse that is as vast and diverse as the very mathematics that govern it. Tegmark's mathematical universe hypothesis challenges conventional notions of existence and reality. It prompts us to consider the multiverse not as a distant theoretical concept, but as a mathematical construct made up of infinite possibilities. This shift in perspective invites deeper questions about the nature of reality itself, suggesting that our universe might be just one of many, each with its own set of rules, waiting to be explored through the lens of mathematics. Meanwhile, the many bubbles interpretation of quantum mechanics, developed by cosmologist Alexander Vilenkin and others, offers yet another fascinating view of reality. Unlike the many worlds interpretation, which imagines the universe continually splitting into multiple branches for each possible outcome of a quantum event, the many bubbles interpretation proposes that the universe is akin to a cosmic foam made up of countless bubbles. Each bubble represents a separate universe that arises from quantum fluctuations within a primordial quantum vacuum. These bubbles may evolve in unique ways, developing distinct physical properties and constants as they go through their own cosmic life cycles. The many bubbles approach offers a more expansive and visually captivating model of the multiverse, focusing on the creation of universes through spontaneous quantum fluctuations. In contrast to the many worlds interpretation, which emphasizes the isolation of universes created from measured outcomes, the many bubbles perspective emphasizes the collective and dynamic process of universe formation. These bubbles could, over time, undergo their own evolutionary paths, shaped by the inherent quantum fluctuations and inflationary processes that drive the cosmos. The result is a vast and ever-expanding multiverse, with universes constantly forming and evolving from the very fabric of quantum reality. This interpretation provides a new way of looking at the multiverse, one where universes emerge not from branching timelines, but from the spontaneous creation of bubbles within a shared quantum landscape. It offers a fresh perspective on how universes might coexist and evolve, framing reality as a dynamic realm of cosmic bubbles, each with its own potential for development and growth. Through this lens, the multiverse becomes not just a collection of parallel worlds, but a living, breathing entity made up of countless, ever-evolving possibilities. The simulated universe theory presents a mind-bending proposition. What if the reality we experience isn't the objective physical world we believe it to be, but a sophisticated computer simulation? This theory has gained significant traction in both scientific and philosophical circles, fueled by technological advancements, artificial intelligence, and a deeper understanding of virtual and augmented realities. Visionaries like philosopher Nick Bostrom argue that as we get closer to creating simulations indistinguishable from reality, it becomes increasingly plausible that we might already be living within such a digital construct. Imagine this. If it were possible for an advanced civilization to generate a perfect simulation, it could raise an even more profound question. Could we, ourselves, be within one of these creations? Advocates of the simulated universe theory suggest that such simulations could be indistinguishable from the physical world, leading to radical implications about our place in the cosmos. If simulations are indeed possible, the theory proposes that an advanced civilization, whether human or alien, could have already created vast, complex environments to mirror or explore different versions of reality. And what if there were not just one, but many simulations. This concept introduces the possibility of a multiverse of simulated realities, each created with its own unique rules, laws of physics, and experiences. In this scenario, every simulation could represent a distinct universe with its own history, timeline, and conditions. The creators could, in theory, run simulations exploring countless scenarios, branching out in every possible direction. For instance, imagine a civilization that explores multiple simulations, each one exploring different outcomes based on the decisions made, offering a way to explore what-if scenarios without ever disrupting the foundational reality of the creators themselves. What makes this idea even more fascinating is its intersection with the concept of multiple realities. Each simulation would be a parallel universe operating under different rules but real in its own right. It paints a picture of a multiverse not in the traditional sense, but as a continuum of simulated experiences. This creates an interconnected web of realities that expands beyond our immediate understanding of the universe and its laws. It invites us to think about how interconnected all these potential realities might be and what it would mean for our perception of existence if we were to find out that we were merely one simulation among countless others. Reflecting on the implications of the simulated universe theory challenges the very foundations of our understanding of existence. If we are indeed living in a simulation, then questions about the nature of consciousness, reality, and what constitutes a real experience take on new meaning. Whether we inhabit a physical universe or a digital one, the boundaries between the two become increasingly blurry. This blurs our understanding of what is truly real, as each simulated experience is just as valid as a physical one. The theory invites us to explore the infinite possibilities and alternative paths that existence can take, opening up profound philosophical questions about our place in the cosmos. Parallel to this concept is modal realism, a philosophical theory proposing that every possible world is just as real as the actual world we experience. In the realm of modal realism, every conceivable version of the universe exists in its own parallel reality, with each alternative world reflecting a different choice, event, or outcome. This connects neatly with the idea of the multiverse in physics, especially when looking at quantum mechanics. One of the key interpretations of quantum mechanics, the many worlds theory, suggests that every quantum event creates a new branch of reality, each universe representing a different possible outcome. Modal realism and the many worlds interpretation align in their treatment of alternative worlds, offering a framework in which each potential version of reality is equally real. The connection between modal realism and the multiverse theory is clear. Both explore the existence of parallel worlds, whether through philosophical reasoning or theoretical physics. In both cases, the notion that every possible outcome creates its own distinct universe challenges our understanding of reality and existence itself. These theories raise profound questions about the nature of choice, destiny, and the very fabric of the universe, urging us to explore what lies beyond the boundaries of our immediate perception. Whether through simulated universes or the multiverse, the idea of multiple realities is a powerful and intriguing concept that invites us to rethink everything we thought we knew about the world around us. Moreover, both modal realism and the multiverse concept challenge our traditional understanding of a single, unique reality, urging us to rethink the nature of existence. They beckon us to look beyond our immediate experiences, suggesting that what we perceive as real may only be a fragment of a far more expansive network of realities. Modal realism offers a philosophical lens for understanding possible worlds, while the multiverse hypothesis proposes a physical framework for reality's fundamental structure. When we examine these two theories together, they lead us to profound questions about the nature of existence, causality, and the very nature of choice and agency. If all possible worlds exist, as modal realism suggests, what does this mean for the scientific theories that propose separate outcomes branching into alternate universes? These theories, though originating from different fields of thought, converge in their exploration of multiple realities and the implications of choice within them. This intersection invites us to think deeper about how we understand our own actions and their consequences. In such a framework, where every decision spawns a new reality, how do we define personal agency, responsibility, and the true scope of existence? The philosophical and scientific dialogue surrounding these ideas challenges the traditional notion of a linear, singular existence and invites a broader reflection on the vast, layered tapestry of worlds that might exist beyond our current comprehension. The concept of the parallel lives interpretation of quantum mechanics offers an even more captivating perspective on how quantum events unfold. It posits that every possible outcome of a quantum event exists in an alternate, parallel life or timeline for each individual involved. This idea shares some similarities with the multiverse theory in quantum mechanics, but it differs significantly in its approach to the nature of branching universes. In the many worlds interpretation, originally proposed by Hugh Everett III, the universe continuously splits into numerous branches with each quantum measurement, creating a vast multiverse where every conceivable outcome is realized in its own separate universe. These universes are isolated from one another, with no communication or interaction between them, each existing independently, despite originating from a shared past. However, the parallel lives interpretation takes a different angle, focusing on the personal experience of the individual navigating the quantum event. Instead of splitting the universe into distinct, separate branches, this view suggests that individuals experience different outcomes along divergent paths, each determined by quantum randomness. Every person in this interpretation leads parallel lives, each one corresponding to a different set of decisions, experiences, or outcomes. This philosophical lens emphasizes the journey of the individual through a maze of possibilities, raising profound questions about identity, consciousness, and the true nature of choice. What does it mean to make a choice, knowing that each one could lead to a vastly different version of yourself? In this framework, we might explore the idea that our decisions don't merely alter our world, they create new realities, new paths of existence, though we remain unaware of the myriad versions of ourselves that may exist in these parallel realities. This distinction between the many worlds interpretation and the parallel lives interpretation opens up a rich dialogue about the nature of existence. It challenges our conventional understanding of personal identity and raises fascinating questions about the consequences of our actions. If every decision leads to a separate reality, how does this shape our sense of self and our understanding of free will? As individuals, how do we navigate a world where every choice branches off into infinite possibilities? These thought-provoking ideas contribute significantly to the broader conversation within the philosophy of science, prompting deeper reflections on the intricacies of consciousness and existence itself. The theory of quantum suicide and immortality, which builds upon the foundations of quantum mechanics, introduces yet another intriguing element to this discussion. Viewed through the lens of the many worlds interpretation, the theory explores a hypothetical scenario in which an individual conducts a series of experiments that involve making decisions, some of which could lead to death or survival. In this thought experiment, the person might engage with a quantum device, a mechanism that has a probability of causing fatal outcomes, like the decay of a radioactive atom. As the individual repeatedly conducts the experiment, quantum mechanics dictates that every possible outcome occurs in a separate universe. If the person survives, they continue to exist in one branch, while in another, they perish. From the perspective of the individual involved, this experiment would unfold as a continuous cycle of survival with no fatal outcome in sight. Each time the experiment is repeated, the universe splits, and in one version they survive while in another they do not. This scenario could theoretically result in a form of immortality, in which the individual never experiences death because there will always be a branch in which they continue to exist. This unsettling but captivating framework challenges our understanding of mortality and consciousness. If one could always survive in at least one branch of the multiverse, what does this mean for the nature of life, death, and existence itself? Does immortality lose its meaning if it is infinite, spread across an endless number of realities? In the end, these theories, modal realism, the multiverse concept, the parallel lives interpretation, and quantum suicide, invite us to reevaluate the very fabric of existence. They stretch the boundaries of our comprehension and raise more questions than they answer. But in doing so, they reveal the limitless potential of reality, encouraging us to consider that the universe we experience may be just one of many, with countless other lives, choices, and outcomes waiting to unfold in parallel dimensions. These ideas challenge the way we view reality, identity, and even mortality, pushing us to expand our minds and consider the infinite possibilities that lie beyond the visible world. In exploring the many worlds interpretation, one is faced with an intriguing and paradoxical idea. What if quantum suicide experiments conducted over and over again never lead to a definitive death? In this interpretation, an individual may continue to exist in the branches where they survive, leading to a remarkable conclusion. Within those surviving branches, the individual is effectively immortal. From their own point of view, they will never experience death. This idea opens up profound questions not just about the mechanics of quantum physics, but also about the nature of existence, identity, and consciousness. What does it mean to be alive when death becomes a mere illusion, a concept that exists only within the confines of specific branches of reality? The many worlds interpretation invites us to reconsider our fundamental understanding of reality itself. It suggests that every action, every event, every moment of decision creates new branches in a vast multiverse. In these separate branches, the outcomes of choices diverge, allowing for multiple versions of ourselves to exist, each in its own timeline. The notion of immortality in this quantum context is tantalizing. Could we ever truly die if, at every instance of possible death, there's always another version of us that continues? And if we accept this possibility, what does it say about the fluid nature of consciousness, constantly shifting and expanding across a never-ending series of parallel worlds? These reflections blur the lines between what we perceive as life and death, forcing us to confront the complex interplay between fate, free will, and the quantum realm. This brings us to another fascinating concept, the cyclic model of the universe. In stark contrast to the linear view of time that we often take for granted, the cyclic model proposes an eternal sequence of cosmic expansions and contractions. The universe, in this framework, experiences endless cycles of birth, evolution, and rebirth. It begins from a dense, hot state similar to the Big Bang, then expands until it reaches its maximum size. But rather than continuing indefinitely, it eventually begins to contract, collapsing back into a singularity before the entire process begins anew. This model challenges our conventional understanding of the universe as a one-time creation, offering instead the idea of an ever-repeating cycle with no definitive beginning or end. It suggests that the universe is not a static entity, but a dynamic, ever-evolving system that has been and will continue to be shaped by forces far beyond our comprehension. What is particularly fascinating about the cyclic model is its implications for the existence of multiple universes. As the universe expands and contracts, it undergoes changes in its physical properties, its laws, and even its dimensions. Each new cycle could represent a completely different iteration of the universe, with its own set of rules and realities. In this sense, the universe we inhabit might be just one phase in a larger, ongoing series of universes. The transition from one phase to another could give birth to entirely new realities, each one uniquely shaped by the cosmic fluctuations that preceded it. The cyclic nature of the universe opens the possibility that our reality is not the only one in existence, and that multiple universes, each with its own characteristics, could coexist, all emerging from the remnants of the last. This model dovetails with ideas from inflationary cosmology, which suggests that rapid expansion could create bubble-like structures in a larger multiverse scenario. Each contraction phase could produce quantum fluctuations, triggering new Big Bangs that give rise to entirely new universes. These new universes could either exist alongside our own or emerge from it in ways we cannot yet fully grasp. If this is true, then not only is our universe one of many possible iterations, but it is part of a grander cosmic evolution, a process of continual rebirth on a scale that transcends our comprehension. The implications of the cyclic model are staggering. They challenge our most basic understanding of time, existence, and reality. Could time itself be cyclical, with no true beginning or end? Are we simply one phase in an eternal cosmic dance? This model forces us to rethink the nature of existence, pushing the boundaries of what we understand about the cosmos and our place within it. If these cycles are infinite, then the universe becomes a much grander entity, a participant in an endless loop of cosmic evolution, with each phase giving rise to new realities. The very notion that the universe could be part of a larger, ever-evolving framework invites us to reconsider everything we thought we knew about the nature of reality. Parallel to this is the Big Bounce theory, which offers an alternative perspective to the traditional Big Bang model. According to the Big Bounce, our universe is not the product of a singular explosion, but rather part of an ongoing cycle of cosmic expansions and contractions. Each contraction brings the universe to a highly dense state, possibly resembling a singularity. But rather than ending, this dense state triggers a rebound, a bounce, that starts the expansion phase anew. In this view, the universe we currently inhabit is simply one phase in an endless series of cosmic rebirths. This theory suggests that previous universes may have existed before our own, each one contributing to the unfolding story of the cosmos. These past universes could have had entirely different physical properties, laws, and dimensions, adding layers of complexity to the grand cosmic tapestry. Furthermore, the Big Bounce theory challenges the uniqueness of our own universe, proposing that it is but a part of a larger, infinite multiverse that has been cycling through time for eons. This idea forces us to reconsider our place in the cosmos, not as a singular, isolated event, but as part of a much larger, ongoing cosmic narrative that stretches far beyond our current understanding. In both the many worlds interpretation and the cyclic model of the universe, we find ourselves confronted with profound questions about the nature of existence, identity, and the boundaries of time and space. These ideas offer us glimpses into a reality far more complex and mysterious than we could have ever imagined. They remind us that the universe is not a static, unchanging entity, but a dynamic, ever-evolving system that challenges our perceptions of life, death, and the very fabric of reality itself. Additionally, the Big Bounce theory invites a radical expansion of our understanding of the cosmos. It is not merely a challenge to the conventional theories of cosmic origin, but a bridge that integrates cutting-edge concepts from quantum gravity. This field delves into the profound relationship between gravity and the subatomic world, where the fabric of space-time is influenced at the tiniest scales. The marriage of these ideas presents an intriguing possibility: a universe in perpetual flux, oscillating between phases of expansion and contraction. Each cosmic cycle, from collapse to reemergence, could give birth to entirely new realities. This continuous transition between states holds the potential to reshape our understanding of time and existence itself. The Big Bounce doesn't just disrupt our perceptions of the universe's origin, it raises questions about the very nature of time. What if the cosmos has no definitive starting point, but instead is a series of endless rebirths, with an infinite number of universes rising and falling in unbroken cycles? These cycles of cosmic evolution may not be isolated, but instead interconnected, with each new iteration building upon the last in ways we are only beginning to understand. One of the most compelling alternatives to traditional cosmological models is Roger Penrose's theory of conformal cyclic cosmology, CCC. Penrose introduces an entirely new perspective on the evolution of the universe, one in which the cosmos progresses through infinite cycles, each known as an eon. In his vision, the end of one eon flows seamlessly into the beginning of the next, creating a continuous cosmic cycle that challenges the conventional narrative of a singular Big Bang event. Unlike the familiar view of the universe as a one-time occurrence, CCC paints a picture where the universe undergoes periodic phases of expansion and transformation, each connected to the others in an unbroken cosmic narrative. At the core of this theory is the idea of conformal geometry, a mathematical framework that simplifies the structure of the universe. As the universe expands and cools, the scale of distances and the physical properties of matter diminish, gradually becoming less significant. Eventually, Penrose theorizes, the universe will reach a point where, at the end of an eon, it is largely empty, composed primarily of low-energy radiation. At this stage, space and time lose their usual characteristics, and the universe enters a state of cosmological recycling, paving the way for the next cycle. This moment of transition holds great significance in Penrose's theory. He suggests that the gravitational waves and dynamics of the previous eon encode information that carries over into the next cycle. While each eon may appear completely distinct in terms of matter, the underlying structure of spacetime remains linked, enabling the formation of new galaxies and cosmic phenomena in the subsequent eon. Through this lens, the universe is not a one-off event, but an ongoing series of connected cycles, each building on the knowledge and dynamics of the one before it. Penrose's conformal cyclic cosmology challenges not only the traditional Big Bang theory, but also the idea of an eternal universe. It proposes a vision of the cosmos in which each eon represents a chapter in a much larger cosmic narrative, one in which time itself is fluid and ever-evolving. These cycles are not merely repetitions, but opportunities for new creations, with each eon leaving echoes of the previous one while forging a path into the unknown future. Through this perspective, the universe's history is seen as an unfolding saga, one that transcends conventional time and opens up new possibilities for what the universe and existence itself might ultimately become. Parallel to this, the oscillating universe model offers another intriguing framework. This model envisions a universe that constantly expands and contracts, undergoing infinite cycles of creation and destruction. According to this theory, the universe expands until it reaches a peak size, only to contract again, collapsing into a singular state before bouncing back into another expansion phase. Each of these cycles, or oscillations, results in a new universe with distinct characteristics and physical properties influenced by the conditions surrounding its contraction and subsequent rebirth. The idea of a universe that undergoes periodic cycles of creation and destruction offers a stunning implication. Each cycle could represent a new iteration of the cosmos, with entirely unique conditions, yet still subtly influenced by the dynamics of its predecessor. This vision paints the universe as a continually evolving entity, with each oscillation giving rise to a distinct reality. As the universe contracts, it may lose much of the information and properties of the previous phase, allowing for fresh conditions to emerge during its next expansion. Each new iteration of the cosmos is thus both a continuation and a reinvention, a reflection of its past, yet shaped by entirely new forces. The possibility of multiple universes emerging over time is further supported by the concept of quantum fluctuations during the expansion phases. These fluctuations could give rise to new states of matter, energy, and even fundamental constants, which would, in turn, create entirely different types of universes. Each cycle could produce a universe with unique properties, universes that differ not only in their physical structure, but also in their fundamental nature. In this framework, our current universe is but one instance in an infinite sequence of oscillating realities. Each cycle is a new manifestation of cosmic evolution, with echoes of the previous ones resonating through time. The idea of a universe constantly oscillating, rebounding from one cycle to the next, challenges our understanding of singularity and permanence. It suggests that the universe we know may just be one of countless iterations, each cycle an opportunity for new realities to emerge, shaped by the unpredictable dynamics of the cosmos. Ultimately, both the Big Bounce and models like Penrose's conformal cyclic cosmology or the oscillating universe propose a profound shift in how we view the universe's existence. Instead of seeing the cosmos as a one-off event, these theories present it as an eternal, dynamic process, one that transcends conventional ideas of time and space. What if, in the grand scheme of the universe, each life cycle is merely a chapter in an ongoing story, written across the vast expanse of time? Perhaps the true nature of existence is far more expansive, mysterious, and ever-changing than we could ever imagine. The oscillating universe model offers a profound challenge to the traditional understanding of the cosmos, particularly the idea that the universe had a fixed beginning and will eventually meet a definitive end. Instead, this model envisions a universe in constant flux, a never-ending cycle in which universes are born, evolve, and eventually fade into oblivion, only to be replaced by new universes in an eternal loop. This cyclical process hints at a deeper cosmic rhythm, one that spans the vast expanse of time, suggesting that our universe might not be a solitary entity, but a part of an ongoing interconnected flow of realities. Within this grand cosmic dance, multiple universes could emerge, evolve, and vanish, each one following a unique trajectory yet bound by the same rhythm. As we delve deeper into the workings of this idea, we uncover the emergent cyclical inflation model, which offers an equally captivating perspective on the origins and evolution of the universe. This theory proposes that the cosmos is not born from a singular one-off event, but instead undergoes a continuous sequence of expanding and contracting phases. Central to this model is the concept of inflation, a period of rapid, exponential expansion of space that took place shortly after the Big Bang. However, the cyclical inflation model takes this idea further, proposing that the universe has undergone multiple cycles of expansion and contraction, not just once, but endlessly throughout its existence. Each cycle begins with a rapid inflationary phase, which stretches space beyond imagination, smoothing out any irregularities and forming a uniform universe. Once inflation subsides, the universe enters a contraction phase, gradually collapsing back into a dense, high-energy state. When this dense state is reached, the cycle begins anew with another inflationary burst, leading to the expansion of a new universe. This ongoing process presents the universe as a never-ending rhythmic dance of creation, destruction, and recreation. One of the key strengths of the emergent cyclical inflation model is its ability to provide explanations for some of the most perplexing mysteries surrounding the Big Bang and cosmic inflation. It offers a way to understand the homogeneity and isotropy, the uniformity in space, observed in the universe today, without relying solely on a single explosive event. Additionally, this model may offer answers to ongoing questions related to dark energy and the ultimate fate of the universe. As scientists continue to explore this theory, it brings forward intriguing questions about the nature of time, space, and the very structure of reality itself. This blending of inflationary theory with a cyclic model of the cosmos presents a compelling narrative, one that not only challenges conventional wisdom, but opens up entirely new pathways for understanding the universe and our place within it. Yet, within this grand cycle, the concept of entropy presents a significant puzzle. Entropy, which is the measure of disorder within a system, is governed by the second law of thermodynamics, stating that entropy tends to increase over time in an isolated system. In this view, the universe should gradually descend into chaos and disorder. But in the cyclical models of the universe, the question arises, how is entropy managed as the universe undergoes endless cycles of expansion and contraction? How can the universe continually reset itself, avoiding the inevitable decline into disorder? One possible explanation lies in the notion that entropy is reset at the beginning of each cycle. As the universe inflates from an intensely dense state, the entropy is essentially wiped clean. This reset allows the universe to start anew, creating conditions that could support the development of complex structures and even life, without the burden of accumulated disorder from previous cycles. This process could involve the compression of all matter and energy during the contraction phase, followed by a fresh low-entropy state as the universe begins to inflate again. Another intriguing possibility is that entropy could be redistributed during the contraction phase. Rather than simply building up over time, the universe might allow entropy to reorganize itself as it collapses. In this phase, some of the disorder accumulated in previous cycles could be transformed into new forms of order. This could allow the universe to maintain a balance, continually renewing itself through its cyclical transitions that are giving rise to new structures and systems, even as the old ones dissolve. In this intricate process, the universe would not be descending into chaos, but rather engaging in a delicate balance of entropy and order. Through the cyclical transitions of expansion and contraction, the universe could keep reinventing itself, continuously creating and recreating the complex and structured systems that define it. It would be a cosmic rhythm of birth, death, and rebirth, one that holds the potential for infinite renewal. Moreover, scientists continue to delve deeper into the mechanisms that might enable transitions between the vastly different phases of the universe. Concepts such as quantum gravity and modifications to traditional thermodynamic laws are gaining traction within the framework of a cyclic universe. These ideas offer a fascinating opportunity to rethink how we understand and manage entropy in a universe that undergoes endless cycles of expansion and contraction. Rather than viewing entropy as a one-way arrow, these new approaches suggest a dynamic, multifaceted perspective, one that aligns with the unique behaviors of a cosmos that forever oscillates between vastly different states. At the core of any theory about the universe is observational evidence. It serves as the critical gauge for validating or potentially refuting theories, including those surrounding cyclic models. One of the most essential aspects that cyclic universe models aim to explain is the cosmic microwave background, CMB radiation. This remnant glow, left over from the early universe, offers a snapshot of the cosmos shortly after the Big Bang. If our universe indeed cycles through multiple expansions and contractions, astronomers may look to the CMB for specific signatures that suggest a repetitive cosmic rhythm. These patterns could reflect the very cycles of the universe, showing up as anomalies or irregularities in temperature fluctuations. By carefully studying these distortions, scientists hope to uncover clues that either support or challenge the cyclic nature of the cosmos. Another key factor to explore is the large-scale distribution of galaxies and cosmic structures. These formations are not randomly scattered, but instead form intricate patterns across the universe. If the universe cycles, as some models propose, we might expect to observe certain regularities in the way galaxies cluster together or in the voids between them. Cosmic structures shaped by past cycles could manifest in specific statistical patterns that researchers could detect through expansive sky surveys. These patterns might tell the story of the universe's cyclical nature, pointing to signs of previous expansion and collapse phases embedded in the very fabric of the universe. Equally vital to understanding the cyclic model is our knowledge of dark energy. This mysterious force remains one of the greatest puzzles in modern cosmology. How dark energy influences the universe's expansion could provide a critical piece of the puzzle. If the universe follows a cyclical path, we might observe fluctuations in dark energy's influence during the transitions between the expansive and contracting phases. A careful study of these variations could lend strong support or offer convincing counterarguments to the notion of a cyclic universe. Finally, gravitational waves offer a cutting-edge tool for testing cyclic universe theories. These ripples in space-time, generated by cosmic events like the collision of black holes, can carry information about the conditions under which they were produced. By studying the frequencies and patterns of these waves, scientists might identify specific signatures that align with the predictions of cyclic models. If gravitational waves display characteristics expected from previous cycles, it could significantly strengthen the case for a universe that follows a repeating cyclical pattern. In this sense, gravitational waves might not only reveal more about the current state of the cosmos, but also provide a direct connection to its past cycles. Each of these observational avenues, whether through the study of the CMB, the distribution of galaxies, dark energy, or gravitational waves, offers a rich potential for advancing our understanding of the universe. They hold the promise of confirming or challenging the idea that the cosmos operates in a cyclical fashion. As we gather more data and refine our methods of observation, we edge closer to an answer that could redefine our understanding of cosmic evolution. Cyclic models also present compelling alternatives to the traditional initial singularity problem, which has long been a cornerstone of cosmological theory. The singularity, a point of infinite density and temperature, marks the supposed beginning of the universe in current models. However, this concept raises profound questions because at such extreme conditions, the laws of physics as we understand them break down. Cyclic models propose a bold shift in thinking, suggesting that rather than emerging from a singularity, the universe undergoes an eternal series of cycles, periods of rapid expansion followed by eventual contraction. This idea bypasses the need for an origin point, suggesting instead that the universe has always existed in some form, transitioning through epochs of growth and collapse. In this vision, each cycle begins from a highly dense state, but crucially, this state does not entail an infinite singularity in the classical sense. Instead, it reflects a finite volume of matter and energy. The transition between contraction and expansion, far from being a violent rupture, suggests a smooth evolution of the universe's physical properties. Some cyclic models also integrate insights from string theory and quantum gravity, areas of physics that explore the behavior of fundamental forces at extreme scales. These theories propose that at incredibly high densities, the universe's fundamental forces and particles may exhibit unusual behavior, potentially eliminating the need for an infinite singularity. In these models, a bounce could occur, where the universe contracts to a point only to rebound into a new phase of expansion, reshaping our understanding of what a beginning or an end could mean in cosmological terms. The question of time itself is central to cyclic universe models. In traditional cosmology, time is seen as having a singular origin, beginning with the Big Bang. However, cyclic models challenge this notion by suggesting that time is cyclical, with no true beginning or end. Instead, time could be a continuous loop, with each cycle of expansion and contraction marking a new phase in a broader, eternal rhythm. In this view, the universe is not a one-time event, but an ongoing process, ever cycling through infinite phases. This perspective redefines our understanding of cosmic existence, urging us to think of time not as a linear progression, but as a series of interconnected cycles, each one building upon the last. Finally, the concept of time before time presents an intriguing paradox within the framework of cyclic universe models. In traditional cosmology, time is considered to have started at the Big Bang, a distinct event marking both the beginning of the universe and the flow of time itself. But what if time stretches backward endlessly, with no ultimate origin? What if the universe in its cyclical nature has no true beginning, only an eternal recurrence of phases, each one linked to the next? This idea turns our conventional understanding of time on its head, suggesting that the universe could exist without a singular, finite starting point, and time itself might be far older and more complex than we've ever imagined. However, cyclic models challenge the conventional view of time and suggest that our understanding of the cosmos may be far more intricate than we realize. Instead of viewing time as a linear progression with a definitive beginning, these models propose that time could be an eternal cycle with no singular starting point in the way we typically think of it. In this view, the universe is locked in a continuous loop of expansion and contraction, where each cycle represents a different phase of existence. The concept of time before time emerges within these models, hinting at epochs or phases that predate our current cosmic expansion. If the universe is perpetually undergoing cycles, expanding, contracting, and repeating, then both space and time can be seen as locked in an endless, dynamic dance. These cycles may stretch back across countless iterations of before and after, challenging our most basic assumptions about the nature of reality. In such a framework, time does not begin with the Big Bang. Rather, it is intrinsically connected to the entire history of the universe's cycles. Each contraction phase leads seamlessly into a new expansion, meaning there are moments that precede what we currently define as now. This cyclical nature of the universe invites us to reconsider the very fabric of time itself, suggesting that time might be a continuum with no definitive beginning or end. Past cycles, with their own unique conditions and phenomena, may have set the stage for the universe we experience today. Furthermore, emerging theories in quantum gravity and string theory add complexity to this view. These advanced models hint that under conditions of extreme energy and density, time could behave in ways that defy our standard perceptions. Time, under such conditions, might not behave as we expect, allowing for possibilities far beyond our familiar understanding of the universe. In this way, the idea of the cyclic universe offers a fascinating narrative that intertwines time with the very fabric of existence. It suggests a universe with a layered temporality, one that transcends any single beginning, offering a vision of reality that is far more intricate than we typically envision. This complexity is further explored through the lens of the anthropic principle, which asserts that the universe's properties must allow for the existence of observers like ourselves. At its core, the anthropic principle proposes that the universe is uniquely tuned to support life, and it is this property that makes life and consciousness possible. Within the context of cyclic models, the anthropic principle takes on a distinct new dimension. It suggests that the universe we inhabit has evolved through countless cycles, each one giving rise to conditions that could foster the emergence of complex structures in life. As the universe expands and contracts, it forms galaxies, stars, and planets, creating environments where life might flourish. The anthropic principle, then, could be used to argue that the reason we find ourselves in a universe capable of supporting life is not a fluke, but a natural outcome of this cyclical evolution. Previous cycles, perhaps less hospitable, might have failed to produce the conditions we now experience, meaning only those universes that eventually gave rise to life have survived. Moreover, cyclic models suggest that across different cycles, the laws of physics and cosmological conditions could vary significantly. Each cycle may produce a unique universe with its own set of parameters and possibilities. This idea allows for the concept of a multiverse, where our universe is just one of many, each shaped by the cycles that preceded it. The anthropic principle helps to frame this idea, suggesting that we exist in a universe where life is possible because out of the infinite variety of possible universes, this one, by sheer chance or necessity, supports life and consciousness. Thus, the cyclic universe model offers an intriguing, complex view of both time and existence, blending deep cosmological questions with the mystery of life's emergence in the universe. It invites us to reconsider not just the past, but the very nature of time and reality itself, painting a picture of a universe far more ancient and varied than our linear models could ever suggest. In the world of cosmology, there exists an intriguing idea: cyclic models of the universe. These theories explore the possibility that the laws of the cosmos may evolve or shift during each cycle, creating a universe that constantly adapts. This introduces a compelling notion. The specific conditions we observe today may not be a singular event, but rather the result of countless cycles refining and honing the universe into a form capable of supporting conscious life. At the heart of this idea lies a powerful interaction between cyclic cosmology and the anthropic principle. The anthropic principle suggests that the universe is not just evolving in a random fashion, but in a way that appears to foster the development of conscious beings. It implies that the universe's evolution may not be accidental. Instead, it may be inherently shaped to increase the likelihood of conscious life arising, reinforcing the delicate connection between cosmic evolution and our very existence. This fascinating link raises the question: is the universe's design the result of sheer chance, or is it finely tuned to allow life to emerge? Meanwhile, there are cosmologists who look beyond the edge of the observable universe, intrigued by the possibility that the laws of physics may not be the same everywhere. Our observable universe is limited, extending only as far as light and other signals have had time to travel since the Big Bang. Beyond this boundary, a vast, uncharted expanse stretches out into the unknown. It's a region that we cannot see, but that might harbor conditions far different from those we experience. The potential existence of differing physical laws in these unseen realms opens up fascinating possibilities. Imagine the possibility that physical constants, the very building blocks of the cosmos, are not uniform throughout the universe. Some theories, such as cosmic inflation, suggest that different regions of the universe may have evolved under vastly different conditions. In these areas, the fundamental forces of nature, gravity, electromagnetism, and even the behavior of particles might differ entirely from our own experience. Such differences could lead to completely distinct physical laws in distant parts of the universe, transforming what we understand as reality. Adding another layer of complexity is the multiverse theory, which posits that our universe is only one among many, perhaps even an infinite number of universes, each governed by its own set of physical laws. In this model, regions beyond our observable universe could belong to entirely separate bubble universes, each disconnected from ours. If this hypothesis holds, the laws that seem constant to us may be mere local constructs, applying only within the confines of our universe. In this framework, other universes could exhibit radically different laws, expanding our understanding of what is possible in the vast expanse of reality. Even more mind-bending is the way time and space might behave in regions beyond our observational limits. The effects of cosmic inflation suggest that in these unseen realms, quantum fields, gravitational forces, and the very fabric of space-time could behave in ways we cannot yet comprehend. extreme curvature, or other unknown factors could radically alter fundamental interactions, producing realities that are unrecognizable from our current perspective. The very notion that the laws of physics might change beyond the edge of the observable universe challenges everything we thought we knew about the cosmos. It forces us to confront the limitations of our current understanding, opening the door to new theories and possibilities. As scientific exploration continues and new discoveries are made, our understanding of these distant, uncharted realms may dramatically shift, reshaping our view of reality itself. It could redefine how we perceive space, time, and the fundamental forces that govern our existence. One of the most intriguing mysteries in modern cosmology is the fine-tuning problem. This refers to the startling fact that the fundamental constants of nature, such as the strength of gravitational and electromagnetic forces, are astonishingly well-suited for life. If these constants were even slightly different, the universe would be inhospitable to the complex structures that life depends on. This remarkable precision has led to profound questions about the nature of the universe and how it came to be so finely tuned. One possible answer to the fine-tuning problem is the multiverse hypothesis. According to this theory, our universe is merely one of a vast collection of universes, each with its own set of physical constants and laws. In such a scenario, the diversity of universes allows for a wide range of conditions, some of which would not support life at all. The multiverse theory suggests that, in the grand scheme of things, it's statistically probable that at least one universe, ours, would happen to have the exact conditions necessary for life to emerge. By expanding the scope of the universe to include multiple realms, the multiverse theory reframes the fine-tuning issue. It suggests that our universe, while seemingly finely tuned, is just one of many, and that life-friendly conditions are simply one of many possibilities. The existence of conscious beings like us becomes more plausible when viewed from this broader perspective. We naturally find ourselves in a universe that permits life, while other, less hospitable universes remain uninhabited and undetected. This multiverse idea, while speculative, offers a fresh perspective on the mysteries of existence. It invites us to consider that the precise conditions necessary for life may not be the result of some grand design, but rather a cosmic accident, part of a broader, unpredictable tapestry of universes. And in this vast, infinite expanse, our universe, with all its fine-tuning and delicate balances, may simply be one small part of a far larger and more complex cosmic story. The concept of the multiverse has long sparked fascination and debate in scientific circles, offering a bold new perspective on the nature of reality. Some versions of the multiverse theory propose mechanisms that might give rise to the divergence of fundamental constants across different universes. For instance, certain theories of cosmic inflation and string theory suggest that distinct regions of space might undergo unique processes impacting their physical properties in diverse ways. As a result, the multiverse not only presents a potential solution to the age-old fine-tuning problem, but also pushes the boundaries of our understanding, prompting deeper inquiries into the very fabric of existence. By considering our universe as part of a vast, interconnected tapestry, scientists explore how variations in fundamental constants could be intrinsic to the very structure of the cosmos. In this scenario, the strength of fundamental forces, such as gravity and electromagnetism, could vary dramatically across different universes. In our own universe, the four primary forces, gravitational, electromagnetic, weak nuclear, and strong nuclear, operate at precisely tuned strengths, creating the conditions necessary for the emergence of matter, stars, galaxies, and ultimately life itself. However, in other universes, these forces might behave in radically different ways, leading to the formation of unique cosmic structures and phenomena. One source of this variation lies in the constants associated with these forces. Take, for example, the gravitational constant, which governs the strength of gravitational interactions. In a multiverse scenario, this constant could differ in other universes, influencing the formation of cosmic bodies. Similarly, the coupling constants that govern electromagnetic and nuclear forces determine how particles interact at the most fundamental level. If these constants were to vary, entire universes could emerge with dramatically different physical properties. In some, gravity might be so weak that stars and galaxies can never form, while in others, the strong nuclear force could be so overpowering that stable atoms cannot exist. Another fascinating aspect of force variability arises from the deeper physical laws and symmetries that underpin these forces. Concepts from string theory, for example, suggest that the forces we observe might be the result of vibrations of fundamental strings in higher dimensional spaces. If the extra dimensions that these strings occupy are configured differently in other universes, the forces in those universes could be shaped by different vibrational modes. This would lead to vastly different expressions of fundamental forces, creating a rich, complex array of possible physical realities. The environment and initial conditions of each universe also play a pivotal role in how these forces manifest. Factors like energy density, temperature, and the overall dimensional structure of a universe could profoundly affect the dynamics of fundamental interactions. For instance, in a universe dominated by high-energy phenomena, the relationships between forces could diverge significantly from those in our own low-energy universe. These variations could give rise to entirely new forms of matter and even exotic, unfamiliar structures in the cosmos. The notion that the strength of fundamental forces might vary across universes opens new pathways for understanding the laws of physics. By investigating these potential variations, scientists are expanding their view of cosmic possibilities and exploring how finely tuned the conditions of our own universe truly are. Such inquiries not only challenge established paradigms, but also deepen our search for the fundamental principles that govern all of existence. Adding another layer of complexity to these ideas is the concept of a variable speed of light. Cosmology traditionally hinges on the assumption that the speed of light is a constant, as described by Einstein's theory of relativity. According to this framework, the speed of light in a vacuum is always the same, acting as an unyielding limit for the transfer of information and energy across the cosmos. Yet the theory of a variable speed of light suggests that this fundamental constant may not be fixed throughout time and space. Proponents of this theory argue that the speed of light could have varied during critical moments in the early universe, or even in entirely separate universes. In this bold cosmological view, light speed might have been significantly higher during the earliest moments following the Big Bang, particularly during periods of rapid expansion, such as cosmic inflation. If light had traveled faster in these early moments, it could have facilitated quicker information transfer across the universe, leading to the large-scale homogeneity we observe today, particularly in the cosmic microwave background radiation. This theory could provide valuable insights into the structure of the universe and the evolution of its fundamental properties. Extending this concept to the multiverse scenario opens up a range of fascinating possibilities. If each universe within the multiverse operates under its own unique set of physical parameters, including the speed of light, then those universes might harbor radically different laws of physics. For example, a universe where the speed of light fluctuates could exhibit gravitational phenomena or other interactions that are unlike anything we experience in our own cosmos. This could give rise to new forms of matter, energy, and cosmic behavior, potentially leading to an even more diverse and intricate understanding of the multiverse. In essence, the theory of variable light speed challenges one of the cornerstone principles of modern physics and offers a fresh lens through which we can view the universe and the multiverse. With each new hypothesis and exploration, scientists inch closer to unraveling the mysteries of reality, reshaping our conception of the cosmos and our place within it. Moreover, the concept of variable speed of light cosmology offers a profound way to address some of the most puzzling phenomena in modern physics. These include mysteries like dark energy and dark matter, enigmatic forces that continue to elude conventional understanding. What if light behaved differently in various regions or universes? Such a change could alter gravitational interactions, influencing how matter clusters and behaves on a cosmic scale. This variability might give rise to new structures in those universes, creating a dynamic, evolving landscape of cosmic evolution. Exploring this idea pushes us to reconsider the fundamental constants and laws that govern our universe. It challenges the rigidity of the physical principles we hold dear, urging scientists to open their minds to the vast possibilities that might exist across different universes. This isn't just about our own cosmos, but about realms that stretch far beyond our observational reach, stretching the boundaries of what we thought was possible. One of the most pivotal elements of our current cosmological model is the ratio of dark energy to dark matter, which plays a crucial role in shaping the universe's expansion and the structure of its vast, complex framework. In our universe, dark energy is believed to account for roughly 70% of the total energy content, while dark matter makes up about 26%. Ordinary matter, the stuff that forms stars, planets, and galaxies, constitutes a mere 4%. But what if this balance is different in other universes? What if these ratios were to shift? Such changes could lead to entirely new cosmic dynamics, creating universes with structures unlike anything we see. In a universe where dark energy outweighs dark matter, we could witness a more accelerated expansion of space, one that occurs too quickly for galaxies and other cosmic structures to form coherently. This could result in a cosmos where galaxies remain isolated, unable to cluster into complex formations. On the flip side, imagine a universe where dark matter dominates over dark energy. In such a scenario, gravitational attraction could reign supreme, pulling matter together and slowing down cosmic expansion. This would likely lead to a universe that has a more clustered distribution of matter and might ultimately collapse back in on itself, creating a vastly different fate for its galaxies, stars, and other structures. But the story doesn't end there. The characteristics of dark energy and dark matter themselves could vary across different universes. What if the laws of physics in other realms lead to a fundamentally different nature for these entities? If dark energy, for example, were altered at a fundamental level, it might no longer exert the repulsive force responsible for accelerating the expansion of our universe. The resulting cosmic dynamics could spark entirely new forms of evolution, shaping star formation, galaxy interactions, and the very fabric of space-time in ways we can scarcely imagine. These variations in the balance of dark energy and dark matter would also profoundly affect the conditions for life to emerge. In a universe where dark energy dominates to an extreme degree, life-supporting environments would be rare, perhaps non-existent. However, in universes with a more balanced distribution of dark energy and dark matter, the conditions might be just right to foster the development of complex organisms. The interplay between cosmic forces, how stars and galaxies form and interact, could pave the way for life to emerge in forms we cannot yet comprehend. By considering the potential ratios of dark energy to dark matter in alternate universes, cosmologists are able to explore a far broader spectrum of possibilities. This line of inquiry sheds light on the forces shaping our own cosmic landscape and points to the extraordinary diversity of realities that could arise from different physical constants and laws. The sheer range of potential outcomes underscores the complexity and wonder of the universe, offering tantalizing glimpses of what might be out there, waiting to be discovered. In this context, the anthropic principle provides a crucial philosophical and scientific lens through which we can examine the conditions necessary for intelligent life. It suggests that the universe must possess specific properties and parameters that make life possible, simply because we exist to observe it. The fine-tuning of the universe the anthropic principle proposes is not a coincidence, but rather a reflection of the constraints imposed by the existence of conscious beings like us. This principle becomes especially significant when discussing the concept of multiple universes, or the multiverse theory. In such a scenario, there would exist an incredibly vast collection of universes, each governed by its own set of physical laws and constants. If this multiverse exists, our universe would simply be one among countless others, some of which may not support life due to inhospitable conditions. The anthropic principle helps explain why we find ourselves in a universe that is just so capable of sustaining life. We are more likely to observe the properties of a universe that can support life because we are here to ask these very questions. Through the lens of the anthropic principle, the apparent fine-tuning of various physical constants makes perfect sense. With countless other universes out there, it's not surprising that at least one, ours, has the right conditions to foster life. This line of reasoning connects the distinct properties of our universe with the broader framework of cosmic possibilities, offering a statistical foundation for our very existence in this vast, mysterious cosmos. The anthropic principle, with its compelling invitation to philosophical reflection, opens up a vast array of questions about the nature of reality itself. It challenges us to reconsider everything we think we know about purpose, existence, and the very structure of the cosmos. When we contemplate the possibility of multiple universes, each governed by its own set of physical laws, a deep and unsettling question emerges. What does this imply about the nature of our own universe, and more poignantly, about our place within it? This exploration goes far beyond the mere physical universe. It reaches into the very essence of life and consciousness. In a universe that may be only one among countless others, each with distinct rules and constants, we are forced to confront profound questions. What are the conditions necessary for life as we understand it? How do these conditions shape our understanding of reality? Take, for instance, the concept of different values for physical constants. These constants, such as the gravitational constant, the strength of electromagnetic forces, and the parameters that govern nuclear interactions, are not merely numbers. They are the hidden architects of everything we observe in the universe. A slight alteration in one of these constants could set off a chain of events with consequences that are hard to imagine. Imagine a universe where the gravitational constant is significantly stronger. The effect would be dramatic. Particles would clump together much more quickly, potentially forming stars and galaxies at an astonishing pace. However, this rapid growth might not be a blessing. While it could foster the creation of larger structures, it would likely destroy the delicate balance needed for the formation of stable planetary systems. In such a universe, the forces of gravity might be too extreme to allow for the nuanced orbits necessary for planets to form, a requirement for complex life as we know it. Now consider a universe where the gravitational constant is much weaker. Here, stars might struggle to form, and without stars, there would be no stable energy sources. The process of synthesizing heavier elements, vital for the formation of planets and the chemistry necessary for life, would be impossible. This scarcity of essential elements would severely limit the formation of the complex structures required for life. Similarly, the strength of electromagnetic forces has profound implications. In a universe where these forces are stronger, chemical reactions could occur at such a pace that stability would be lost. Complex compounds, the building blocks of life, would struggle to form, and the environment would likely be chaotic and hostile. On the other hand, if the electromagnetic forces were weaker, the bonds between atoms and molecules might not be strong enough to support the intricate chemistry necessary for life. These hypothetical scenarios illustrate how incredibly fine-tuned the constants of nature are for the emergence of complex structures, life, and consciousness. The variations of these constants, if explored within the context of other possible universes, offer profound insights into the delicate balance that sustains our own universe. They shed light on the intricate interactions that allow life to exist, pointing to a cosmos that is not only vast, but astonishingly fine-tuned for the emergence of complexity. Now, imagine this delicate balance unfolding across a landscape of multiple universes, each a unique island in an infinitely diverse multiverse. In this view, each universe is an isolated pocket, governed by its own set of laws and constants. Within these island universes, different regions of space-time could operate according to their own rules, leading to a stunning array of cosmic outcomes. Some universes might have a stronger gravitational force, fostering rapid star formation, while others could possess weaker electromagnetic forces, severely limiting atomic interactions. The result would be a multiverse teeming with an unimaginable diversity of physical phenomena. This concept of island universes provides a striking vision of reality, not as a monolithic whole, but as a rich tapestry of possibilities. Each universe in this multiverse might display entirely unique characteristics, leading to alternate forms of matter, distinct energy distributions, and different pathways for the evolution of complex structures. The idea that each universe could evolve independently under different rules expands our understanding of the cosmos, pushing us to think about the very nature of existence and the flexibility of the physical laws that shape it. Furthermore, the theory of island universes aligns with concepts from string theory and quantum gravity. These theories suggest that the fundamental laws of nature may arise from configurations in higher dimensional spaces, and that different regions of space could be influenced by varying arrangements of fundamental strings or fields. This idea challenges our classical understanding of the cosmos, offering the possibility that the laws governing each universe could vary based on these underlying conditions. As if this weren't enough, the existence of these distinct universes raises profound philosophical questions. If there are countless other universes, each with its own set of physical laws, what does that say about the nature of existence? Are we merely one observer in a vast and incomprehensible multiverse? And if so, what is the role of consciousness in such a reality? These questions transcend the physical and venture into the realm of the metaphysical, forcing us to reconsider our place in the grand scheme of things. In addition to the variability of physical laws across different universes, the dimensions of space and time could also vary from one universe to another. In our own universe, we experience three spatial dimensions: length, width, and height, as well as a single dimension of time. But in other universes, these dimensions might be different, or there could be more than three spatial dimensions, or entirely new dimensions altogether. These fundamental differences in dimensionality could radically reshape the very fabric of reality, altering everything from the formation of matter to the emergence of life and consciousness. In the end, the anthropic principle invites us to reflect on the profound nature of reality. It encourages us to consider not just the physical laws that govern our universe, but also the deeper philosophical questions about existence, life, and consciousness in a vast multiverse that stretches beyond the limits of our understanding. Through this lens, reality becomes not just a scientific puzzle, but a tapestry of infinite complexity, full of possibilities that we are only beginning to comprehend. However, various theories in physics propose that our universe might not be the only one, and that other universes could exist, each with different configurations of dimensions and physical laws. These alternate realities could operate according to entirely different principles than the ones governing our own cosmos. For example, string theory suggests that in addition to the three familiar spatial dimensions, length, width, and height, there could be extra dimensions hidden beyond our perception. These additional dimensions might be curled up so tightly at microscopic scales that they remain undetectable to us. Yet, even if imperceptible, their influence could be profound, subtly shaping the behavior of particles and forces at the quantum level. In a universe with more than the usual three spatial dimensions, the fabric of reality itself could be vastly more intricate. Gravity, electromagnetism, and other fundamental forces might not behave as we know them. These extra dimensions could unlock entirely new geometric structures and interactions, revolutionizing our understanding of the universe. For instance, the way matter behaves could be radically different, allowing for new forms of matter, new types of energy interactions, and even new laws of physics. Turning to the nature of time, the situation becomes even more mind-boggling. While we generally perceive time as a single linear flow, moving from past to present to future, some theoretical frameworks suggest that time itself could have more than one dimension. In a universe where multiple time dimensions coexist, the passage of time could behave in ways that defy our understanding. Rather than events unfolding in a straightforward sequence, time could allow for multiple timelines to exist simultaneously, with events occurring in parallel or following varied paths. This could create a reality in which cause and effect are not confined to a linear progression, but instead branch out, intertwining in ways that are impossible to predict. The impact of this concept is profound. A universe with more than one time dimension could fundamentally alter our understanding of causality and order. Perhaps timelines could interact with each other, influencing events across different realities in ways that are not immediately apparent. The conventional understanding of how the universe evolves might no longer hold, with entirely new patterns emerging from the intersection of multiple temporal flows. The configuration of dimensions does not only affect abstract principles like time and space, it also influences the very formation of structures and matter. For instance, in a universe with additional spatial dimensions, the behavior of gravity could differ dramatically, affecting everything from the formation of stars to the development of planetary systems. A world with more than 3 dimensions might offer new possibilities for how celestial bodies come together, how galaxies form, and how cosmic evolution unfolds. Similarly, the presence of extratemporal dimensions could lead to an entirely different understanding of thermodynamics. In our universe, the laws of entropy dictate that systems tend to move from order to disorder over time. But in a reality with more than one time dimension, the concept of entropy itself could be challenged. This could reshape our understanding of how order, chaos, and the passage of time interact. Ultimately, the very idea of different numbers of spatial or temporal dimensions invites us to explore the possibility of radically different realities. These theories push the boundaries of our traditional views of the cosmos and suggest that the universe we observe may be just one of many, each governed by its own set of physical laws and constants. In turn, the exploration of these ideas fuels our imagination, expanding the horizon of what might be possible in the vast multiverse of potential existences. One such idea, the theory of varying fundamental constants, suggests that the constants we consider fixed, such as the speed of light, the gravitational constant, and the fine structure constant, could actually change over time or vary across different regions of the universe. This is a radical departure from the long-held belief that these constants are immutable and universal. If these constants were not fixed, they could influence the laws of physics in unexpected ways. Take the fine structure constant, for example. If this constant were to fluctuate, it could alter the way charged particles interact, leading to changes in the formation of atoms and molecules. Such shifts in the fundamental constants of nature could have profound effects on the chemistry of life, potentially reshaping the conditions necessary for life to emerge or evolve. In fact, certain cosmological observations that don't fit neatly within the current model of the universe might be explained by variations in these constants. But the implications go even further when we extend this idea beyond our observable universe. In a larger multiverse, different regions could each have their own set of constants. This could mean that each universe in the multiverse might operate according to entirely different physical laws. Some universes might have completely different forms of matter, energy, and structures, making them vastly different from our own. The very idea that our universe is just one among many, each with its own constants and laws, challenges our understanding of the fundamental nature of reality. In the end, the exploration of these concepts invites us to rethink the very fabric of existence. If the fundamental laws of physics are not universal, but vary across different realms of reality, it opens up a vast array of possibilities. The study of these varying dimensions and constants not only expands our understanding of the universe, but also stirs the imagination, inspiring us to consider the extraordinary diversity of universes that could exist, each governed by its own set of rules and principles. Studying the potential implications of varying fundamental constants offers scientists an extraordinary opportunity to explore some of the most profound questions about the origins of our universe, its ultimate fate, and the underlying principles governing all of existence. The exploration of these concepts doesn't just challenge the scientific status quo, it broadens our view of the cosmos, suggesting that flexibility and variation might be intrinsic characteristics of reality itself. One of the most tantalizing ideas emerging from this line of thought is the possibility of cosmic wormholes, hypothetical passages through space-time that could potentially provide shortcuts between distant regions of our universe or even connect entirely separate universes. Imagine a wormhole as a bridge woven into the fabric of space-time, allowing for travel across vast distances that, through conventional means, would take millions or even billions of years to cross. The concept of such phenomena first arose from Albert Einstein's theory of general relativity. His groundbreaking equations showed that space-time is not a static, unchanging backdrop, but a dynamic, malleable entity, one that can warp and distort under certain conditions. From this framework emerged the concept of Einstein-Rosen bridges, a theoretical form of wormhole proposed by Einstein and his colleague Nathan Rosen. In this model, two black holes are connected by a tunnel, creating a potential pathway through which matter and information might flow. This bridge-like structure raises fascinating questions. If wormholes truly exist, could they link not only distant points within our own universe, but also serve as gateways to completely different universes, each with its own unique set of physical laws and constants? This idea challenges our very understanding of the nature of space, time, and reality itself. Yet the exploration of cosmic wormholes doesn't stop at the theoretical. The scientific community has already begun pondering what would be required to make these structures more than just mathematical curiosities. For any practical use of wormholes, be it for interstellar travel or interdimensional exploration, overcoming the intrinsic instability that usually plagues them would be essential. This brings us to the idea of exotic matter, a hypothetical substance possessing negative energy density, which might be necessary to stabilize a wormhole and prevent it from collapsing under its own weight. While exotic matter remains firmly in the realm of theory, its existence would fundamentally challenge everything we know about the fabric of reality. The implications of wormholes extend far beyond science fiction. Imagining them as potential conduits between different universes introduces profound questions about the very nature of existence. Could our universe be just one of many, connected by these cosmic tunnels? The potential answers to these questions not only captivate our imagination, but also encourage rigorous inquiry into the deepest workings of the cosmos. The study of wormholes stretches the boundaries of theoretical physics, suggesting that the universe we perceive might only be the first layer of a much larger, interconnected multiverse. As if the possibility of wormholes weren't mind-bending enough, scientists have also theorized the existence of cosmic strings, hypothetical one-dimensional defects that may have formed during phase transitions in the early universe. These strings are predicted to be incredibly dense, yet narrow, stretching across vast swaths of space. They arise from advanced frameworks in string theory and cosmology, hinting that they could play a pivotal role in transforming our understanding of space-time. The connection between cosmic strings and potential pathways to other universes is particularly intriguing. When two cosmic strings come close enough, their immense gravitational pull could warp space-time in such a way that it creates a bridge-like structure between them. This distortion could theoretically form a passage allowing travel from one region of the universe to another, or even from one universe to a completely different one. The interaction between cosmic strings could potentially lead to the creation of string loops, or other configurations of space-time that might serve as doorways to alternate realities, within the framework of a multiverse scenario where each universe has its own distinct physical laws and constants. While these ideas remain speculative, they open up new and exciting avenues for both cosmology and theoretical physics. Understanding how cosmic strings might behave, interact, and possibly influence the very geometry of space-time could provide unprecedented insights into the fundamental nature of the universe. Moreover, this exploration sparks the imagination, allowing us to consider how multiple realities might be interconnected through exotic structures like cosmic strings. The investigation of cosmic strings is more than just an intellectual exercise. It's a key to understanding the grand tapestry of existence. It invites us to imagine a universe far more complex, interconnected, and diverse than we ever thought possible. Through such explorations, we edge closer to unlocking the mysteries of the cosmos, bringing us one step closer to understanding the full complexity of existence itself. Domain walls are theoretical, two-dimensional defects in the fabric of space-time that may form during the phase transitions of the early universe. Similar to the way a bubble forms when water boils, these domain walls arise when different regions of the universe settle into distinct states, each with a unique vacuum energy density. In cosmological terms, the universe could evolve into several phases, each with its own set of physical properties. The boundaries between these phases, referred to as domain walls, mark the transition from one state to another. As we think deeper about the implications of domain walls, their significance becomes even more fascinating. These walls might not only separate different regions of our universe, but also serve as the dividing lines between multiple universes in the broader context of the multiverse theory. Imagine that the universe underwent a phase transition, resulting in multiple vacuum states, each with its own set of physical laws, constants, or even dimensions. In this scenario, the domain walls could act as interfaces, marking the boundaries between these distinct universes. Essentially, these walls could act as barriers that define regions with differing physical rules, potentially leading to entire realities nestled within the vast multiverse. The properties of domain walls could result in profound consequences. For example, if two vacuum states harbor differing laws of physics, crossing through a domain wall could expose you to an environment where the fundamental forces operate in entirely novel ways. This means domain walls might not only separate distinct universes, but also create opportunities for interaction between them, allowing the exchange of energy, particles, or even information, depending on the specific properties of the walls. The study of domain walls remains a largely theoretical field. However, ongoing research is exploring their potential formation, stability, and the role they might play in cosmic evolution. Understanding these defects adds a compelling layer to cosmology, inviting us to question whether our universe is just one of many interconnected realms. The existence of domain walls sparks deep curiosity, offering tantalizing glimpses into the nature of reality and the infinite possibilities that lie beyond the universe we can perceive. Quantum entanglement is one of the most extraordinary phenomena in quantum mechanics. It describes a situation where two particles become intertwined in such a way that the state of one particle instantly affects the state of the other, regardless of the distance between them. This bizarre relationship challenges our classical understanding of locality and separateness, suggesting that information can be exchanged in ways that transcend traditional physical boundaries. As scientists delve deeper into the implications of quantum entanglement, they explore its potential role in linking parallel universes, a central idea in the multiverse hypothesis. This theory proposes that multiple universes could coexist alongside our own. Quantum entanglement may provide a bridge for these universes to connect. In this framework, each universe represents a distinct outcome of quantum measurements, with entangled particles creating a vast web of correlations across different realities. For example, if particles in one universe interact and become entangled, their counterparts in another universe might be affected as well. This could create a complex tapestry of interconnected states, linking various universes in the multiverse. This concept resonates strongly with interpretations of quantum mechanics, such as the many worlds theory, which suggests that every quantum event causes the universe to split into multiple paths, each one representing a different outcome. If particles in these parallel universes remain entangled, they could share information or states, thereby connecting the separate realities. While the idea of quantum entanglement facilitating communication between parallel universes is still speculative and theoretical, it raises important questions about the fundamental nature of reality. How do events in one universe influence or correlate with events in another? And what does it mean for the very fabric of existence if such connections are possible? As researchers continue to explore these questions, the idea of entanglement hints at a reality far more complex and interconnected than we can currently grasp. The concept of brain collisions comes from string theory, where our universe is imagined as a three-dimensional object, called a brain, short for membrane, that exists within a higher dimensional space. In this framework, multiple brains can coexist, and interactions between them might lead to dramatic events, such as collisions. These interactions aren't just theoretical curiosities. They could play a fundamental role in shaping the physical characteristics of our universe and others. When two brains collide, the energy released in the interaction could trigger various cosmic phenomena. For instance, such a collision could create new regions of space-time and potentially even give birth to new universes. This idea aligns with some cosmological models, which suggest that our own universe may have originated from a brain collision, the very moment we call the Big Bang. The effects of these collisions might not only generate matter and energy, but also establish new physical laws and constants in the resulting universes. In this view, the fate of different universes could depend on the type of collision between their respective brains. Each collision might shape a universe's distinct physical properties. from the behavior of fundamental forces to the constants that govern the laws of nature. Thus, brain collisions could hold the key to understanding how the vast diversity of realities in the multiverse comes into being, and how these universes might evolve in tandem or interact with one another in ways we've only begun to imagine. The interfaces formed by brain collisions could serve as boundaries between distinct realms within the vast expanse of the multiverse. Imagine each brain as a universe in itself with its own set of unique properties and laws of physics. These interfaces between the brains could function as transitional zones where the phenomena from one universe interact with those of another. Such interactions could be the conduits for the exchange of information, particles, and even energy, establishing a complex, interconnected web of realities. Exploring the dynamics of these brain collisions propels us into profound and thought-provoking questions about existence, purpose, and the nature of the cosmos itself. It highlights the notion that our universe, far from being an isolated entity, could be a mere part of a grander, interconnected multiverse, enriched by the presence of neighboring brains. Studying these collisions allows us to expand our understanding of fundamental physics while simultaneously pushing the boundaries of imagination, inviting us to contemplate the untold possibilities that might lie beyond the observable universe. A fascinating concept in this theoretical landscape are closed time-like curves, striking constructs from the realm of general relativity that open the door to the potential of time travel. A closed time-like curve is essentially a path through space-time that loops back on itself, meaning an object following this path could return to its own past. This concept stirs up intriguing questions about causality and the fundamental nature of time itself, leading to rich discussions about the implications of such structures on connections between universes in a multiverse scenario. If closed time-like curves exist, they could form pathways linking not just different times within a single universe, but entirely different universes or timelines. Picture this. If a closed time-like curve intersects multiple universes, it could allow a traveler to enter one universe at a specific time and exit in another universe at a completely different time, connecting disparate realities in a way that challenges our traditional understanding of linear causality. The existence of such curves also introduces paradoxes that complicate our notions of time and sequence. One classic example is the famous grandfather paradox. What would happen if someone traveled back in time and prevented their own existence? These complexities have led theorists to wonder whether the multiverse might provide a way out. In such a framework, actions in one universe could generate alternate branches, diverging from the original timeline, thereby enabling time travel without disrupting the consistency of a singular history. While closed time-like curves remain theoretical and speculative, their exploration encourages deep contemplation on the nature of reality itself. What if time, causality, and parallel universes can intertwine in ways that defy conventional reasoning? As physicists and philosophers continue to delve into these ideas, the very fabric of reality becomes an ever more intricate, multifaceted puzzle, one that invites both wonder and caution as we ponder the true nature of the cosmos. The notion of bubble collisions arises from the theory of eternal inflation, which suggests that the universe underwent a rapid exponential expansion during its early moments. According to this theory, different regions of space can stop inflating at different times, forming bubbles where inflation has ceased. Each of these bubbles could contain its own unique set of physical properties, potentially giving rise to different universes within the broader multiverse. When two of these bubbles collide, the event is known as a bubble collision. The consequences of such an event could be dramatic. The collision might generate entirely new forms of matter, energy, or even regions of space-time. In the context of eternal inflation, bubble collisions act as a fascinating mechanism through which different universes could interact, providing pathways for the exchange of physical characteristics or energy, and forming connections between otherwise separate realms. The implications of bubble collisions are vast and thought-provoking. For instance, if our own universe emerged as a bubble during the inflationary period, a collision with another bubble might explain some of the irregularities we observe in the cosmic microwave background radiation or other cosmological phenomena. Each universe's bubble could reflect different initial conditions or physical laws, leading to a diverse landscape of realities where the properties of one universe might influence another. Beyond that, bubble collisions present intriguing questions about the very structure of the multiverse itself. They suggest a dynamic interconnectivity, providing a deeper understanding of how separate universes might share properties, evolve independently, and yet remain linked through these dramatic encounters. This idea reshapes our perceptions of reality, inviting us to think about emergence, symmetry, and diversity in the cosmos, and transforming the way we understand existence itself. Higher dimensions, especially as suggested by string theory and brane world scenarios, offer an equally compelling aspect of theoretical physics. These frameworks propose that in addition to the familiar 3 dimensions of space and 1 of time, there could exist additional spatial dimensions, compactified or otherwise imperceptible to us. The existence of these extra dimensions opens up intriguing possibilities for how they might serve as conduits between different universes. In the context of the multiverse, higher dimensions could provide the underlying structure through which universes interact. Visualize our universe as a 3-dimensional brain embedded within a higher dimensional space. This higher dimensional arena could contain many such brains, each representing a distinct universe, each with its own unique physical laws and constants. The excess dimensions would then offer a medium through which interactions or events transcending the limitations of our familiar 3-dimensional experience could occur. Consider the possibility that if 2 brains were to collide within this higher dimensional space, the interaction might ripple through both universes, altering their configurations. These dynamics could offer new insights into how universes might evolve and interconnect, broadening our understanding of how the cosmos could function on a scale beyond the ordinary 3-dimensional framework we know. As the study of higher dimensions continues to unfold, the implications for the multiverse and our place within it remain a captivating and open-ended frontier in the search for knowledge about the nature of reality. The geometry of higher dimensional spaces could open the door to possibilities beyond our imagination, like shortcuts in the form of wormholes that connect different brains or universes. This idea introduces a fascinating perspective. What if higher dimensions are not just abstract mathematical constructs, but actual pathways allowing particles, energy, or even information to move between different universes? It paints a picture of a vast interconnected multiverse where realities overlap and interactions take place across dimensions we cannot directly perceive. Moreover, these higher dimensions might offer profound insights into the very nature of existence. They could explain phenomena that appear impossible within the limitations of our everyday experiences, events that transcend the boundaries of space, time, and even causality. By exploring the interactions between different universes through a higher dimensional lens, we may unlock the secrets that govern the multiverse, better understanding how it expresses itself in a variety of forms. This exploration doesn't just expand our knowledge of physics, it challenges our fundamental ideas about the very fabric of reality, inviting us to rethink how universes might be interconnected, much like threads woven into a larger, unseen tapestry. At the heart of this theory lies the concept of quantum tunneling, which arises from the strange principles of quantum mechanics. Quantum tunneling refers to the ability of particles to pass through potential energy barriers, even when they don't appear to have enough energy to do so. Unlike classical particles, which follow specific paths dictated by their energy, quantum particles are governed by probabilities. They might show up on the other side of a barrier in ways that defy classical expectations, leading to seemingly impossible outcomes. Taking this idea into the realm of multiple universes suggests a stunning possibility. Quantum tunneling could be the mechanism that allows particles or information to travel between different universes in the multiverse. If our universe is just one of many possible configurations, quantum tunneling might enable a particle to cross the boundary between universes, especially if it finds itself at the edge of a potential barrier that separates them. In this case, the tunnel created by quantum tunneling could provide access to alternate realities, realities that otherwise remain beyond our reach using traditional methods. Mathematically, this idea builds on the wave nature of particles, where each state exists not as a singular point but as a spread-out probability wave. If we think of the separation between two universes as a type of energy barrier, quantum tunneling suggests there is a non-zero probability for certain particles to leap into the neighboring universe. These transitions might be too subtle to observe on a macroscopic scale, but they could show up in specific quantum events, particularly at incredibly small scales. Such transitions might even affect how particles or energy are distributed across the cosmos, opening up new avenues for discovery. While still highly speculative and primarily theoretical, this notion of quantum tunneling between universes provides a compelling framework for considering the deep structure of reality. Rather than viewing universes as separate, isolated entities, quantum tunneling suggests that there may be delicate, probabilistic connections between them, hidden pathways that weave together the fabric of the multiverse. It's a tantalizing prospect that pushes the boundaries of what we know about quantum mechanics, prompting us to reconsider its potential implications for our understanding of the cosmos. One related concept that deepens our understanding of these connections is the holographic principle, which has emerged from theoretical physics, particularly within the realms of black hole thermodynamics and string theory. This principle suggests that all the information contained within a given volume of space might actually be encoded on a two-dimensional surface that defines the boundary of that space. In other words, our three-dimensional reality could be a projection of information stored on a distant, lower-dimensional boundary, much like a hologram creates a three-dimensional image from two-dimensional data. When we extend this idea to the multiverse, the holographic principle suggests that there could be a profound interconnectedness between different universes. If each universe within the multiverse is viewed as a projection from a higher dimensional surface, the boundaries of these universes might carry important clues about their relationships. These boundaries could act as platforms for the exchange of energy or information, meaning that events in one universe could potentially ripple into another. This idea hints at a deeper unity underlying the apparent diversity of realities, suggesting that even the differences we observe between universes might simply be variations in how higher dimensional information is manifested. For instance, if two universes share a portion of their holographic boundaries, it's possible that their physical laws could become subtly intertwined. This could lead to observable effects in one or both of the universes, as the encoded information at their shared boundary influences the dynamics within each. It's a fascinating vision of a multiverse that is not fragmented, but instead intricately connected through layers of higher dimensional information. In this framework, the apparent isolation of universes within the multiverse could be an illusion. Far from being independent entities, these universes may be part of a greater, unified whole, a cosmic network where each universe's identity is shaped by the interplay of higher dimensional forces. By delving into the mysteries of the holographic principle, we might begin to understand the deeper connections that bind the vast, sprawling expanse of realities. Moreover, the holographic principle introduces fascinating questions about the very nature of space-time, urging us to reevaluate core concepts like locality and causality. In this new light, the boundaries of existence may not simply define separateness. Rather, they could act as bridges that allow universes to interact. The implications are profound, as this principle invites us to consider the tantalizing possibility that a deeper interconnected fabric lies at the heart of the multiverse, one that could fundamentally reshape how we understand reality itself. This exploration of the holographic principle fuels ongoing discussions about the universe's underlying nature, suggesting that the cosmos may not be a disconnected series of isolated systems, but part of an intricate, shared structure. This prompts us to question everything we thought we knew about space, time, and the very foundation of existence. One of the most compelling pieces of evidence we have in probing this cosmic interconnectedness is the cosmic microwave background radiation, or CMB. Often referred to as the afterglow of the Big Bang, the CMB is a critical tool for scientists seeking to understand the early universe and its evolution. But what if the CMB is telling us more than we think? Some scientists hypothesize that hidden within its data may lie signatures of other universes, or perhaps traces of interactions with these other realms. This could suggest that we are not alone in this vast cosmos, but part of a more expansive and complex multiverse. A key area of interest involves potential anomalies in the CMB, such as unusual temperature fluctuations or distinct patterns. If our universe had collided with another bubble universe during a phase known as eternal inflation, the remnants of that cosmic clash might manifest as specific anomalies in the CMB. Scientists are particularly focused on identifying temperature variations that deviate from the expected Gaussian distribution. Unexplained cold or warm spots could indicate regions influenced by the gravitational pull of another universe or provide traces of the aftermath of a bubble collision. Another intriguing possibility points to the existence of cosmic strings, hypothetical one-dimensional defects in spacetime. If these strings exist, their immense mass and density could distort the CMB in measurable ways. As cosmic strings warp the fabric of spacetime, they would affect the path of photons traveling through the universe, leaving unique, identifiable patterns or gravitational lensing effects in the CMB data. The detection of such phenomena could reveal new layers of complexity in the universe's fabric, possibly hinting at connections to other realities. Additionally, primordial gravitational waves, ripples in spacetime that date back to the earliest moments of the universe's existence, could leave their mark on the CMB, especially in the form of polarization patterns. These gravitational waves, generated by events such as cosmic inflation, might be further altered by interactions with other universes. Such subtle imprints could offer vital clues about additional cosmic dynamics beyond our observable horizon, pushing the boundaries of our current understanding. The task of uncovering these potential signs of other universes requires an extraordinary level of precision. Scientists are continually improving their observational tools and refining their analytical techniques in order to probe deeper into the CMB and other cosmic data. While the possibility of other universes remains theoretical, the CMB provides us with a crucial observational window, one that could eventually unveil the hidden layers of the multiverse and help us grasp the true scale of existence. Meanwhile, the discovery of gravitational waves has opened an entirely new avenue for exploring the fabric of the universe. These ripples in spacetime, which were first detected in 2015 by the LIGO Observatory, are generated by some of the most energetic events in the universe, such as the collision of black holes or neutron stars. Gravitational waves offer a unique opportunity to probe the deepest recesses of the cosmos, and as the study of these waves progresses, researchers are beginning to consider whether they might provide evidence of a broader multiverse. One fascinating hypothesis is that the gravitational waves produced by such extreme events could be influenced by interactions with other universes. For example, imagine two black holes merging due to a bubble collision between two inflating universes. The resulting gravitational waves could carry a distinctive signature, providing clues about the dynamics of other universes. By analyzing the characteristics of these waves, such as their frequencies and amplitudes, scientists hope to uncover patterns that point to the existence of parallel universes, or at least hint at an underlying connection between different cosmic realms. As our tools for detecting gravitational waves improve, and as we continue to study the complexities of the CMB, we may one day unlock the secrets of a vast and intricate multiverse. This would not only change our understanding of the universe, but also redefine our place within it, challenging the very fabric of reality itself. Gravitational waves, unlike typical forms of energy, carry with them information that transcends the ordinary interactions of matter. These waves are unimpeded by material obstacles. They travel across vast expanses of space without being absorbed or scattered. This unique property means that gravitational waves, especially those generated by cataclysmic events involving multiple universes, could offer us extraordinary insights into the energy levels and properties of other realities. If these waves originated from the collision of branes or the interactions between bubble universes, their detection would be monumental. It could provide compelling evidence for the existence of alternate realms and their characteristics. In fact, gravitational wave backgrounds, the near-constant hum of mergers from distant, violent cosmic events, might reveal a rich and detailed tapestry of cosmic activity. Anomalies or fluctuations in this background signal could hint at interactions with universes beyond our own, especially if there is a correlation between gravitational wave events and electromagnetic data from traditional observational channels. Researchers are actively investigating these possibilities, making connections across various scientific disciplines to decipher the hidden meaning behind this complex data. With the growing sensitivity of gravitational wave observatories, the potential to detect these faint yet profound signals is steadily increasing. Gravitational waves, with their inherent nature, present an exciting avenue for exploring the fundamental composition of our cosmos, possibly opening doors to realms that we can only begin to fathom. This exploration challenges us to confront deep, philosophical questions about the nature of reality, existence, and the unknown realms that may lie beyond our universe. One such notion is that of cosmic bruises, specific anomalies within the cosmic microwave background, CMB radiation, that might serve as evidence of past collisions between our universe and others. These bruises may appear as unusual patterns or temperature fluctuations, indicating interactions that have left a permanent imprint on the very fabric of space-time. The theory behind cosmic bruises suggests that when two universes collide, the energetic interaction could leave an observable signature on the CMB. This imprint, a disturbance in the temperature or polarization of the radiation, could reveal the cosmic aftermath of such a collision. During the inflationary phase of the universe's expansion, if another universe's bubble collided with our own, it could create detectable variations in the CMB, potentially pointing to the presence of another universe and the energetic effects of their cosmic encounter. In this search for cosmic bruises, scientists look for localized areas within the CMB that diverge from the expected uniformity. These regions may be evidence of where two universe bubbles collided, creating ripples in space-time that are recorded in the cosmic background. Identifying these cosmic bruises could provide strong evidence for the theory of eternal inflation and the broader concept of the multiverse. As researchers delve into this vast and intricate data, their tools and technologies are becoming ever more advanced. These advancements give them the ability to detect even the smallest variations in the CMB, improving their chances of uncovering the subtle effects of cosmic interactions. Cosmic bruises could not only shed light on the history of our own universe, but also offer a window into the interconnectedness of a multiverse. This ever-expanding pursuit captivates the scientific community, urging us to consider the vast and enigmatic realities that may exist beyond our observations. Simultaneously, quantum mechanics offers another promising route for detecting the existence of parallel universes. The study of quantum phenomena, such as superposition, the ability of particles to exist in multiple states simultaneously, could offer clues about multiple realities coexisting alongside our own. As measurement techniques advance, scientists are gaining the ability to explore superposition with unprecedented precision. This could reveal evidence of branching realities, potentially pointing to the existence of parallel universes. Moreover, quantum entanglement, the phenomenon where particles become intertwined and influence each other, regardless of the distance separating them, may hold the key to understanding how these universes interact. Enhanced measurement capabilities could allow researchers to explore entangled particles in greater detail, looking for correlations and effects that cannot be explained by traditional quantum models. Unexpected or inexplicable results in these experiments could point to the influence of parallel realities, suggesting that our universe is part of a much larger, more interconnected multiverse. As scientific tools become more advanced, and researchers push the boundaries of our understanding of quantum mechanics, we may soon find ourselves on the verge of discovering tangible evidence for the existence of parallel universes, unseen dimensions that influence the very fabric of our reality. The potential to explore these connections in the quantum realm offers one of the most thrilling prospects in the ongoing search for the ultimate nature of the cosmos. Moreover, the continued advancements in quantum computing hold immense promise in the realm of exploring the multiverse. These breakthroughs could pave the way for simulations of quantum systems with unprecedented accuracy, enabling us to model complex interactions that more closely mirror the potential behavior of parallel universes. By simulating how quantum states correlate across various branches of reality, researchers could gain valuable insights into the nature of these universes and perhaps how they might interact with one another. If experimental results begin to align with the predictions made by these sophisticated models, it could serve as indirect evidence for the existence of parallel universes. As quantum measurement techniques evolve, they may unravel the fascinating interplay between reality and the underlying principles of quantum mechanics. The study of quantum behavior could not only deepen our understanding of the universe itself, but also offer compelling evidence for the existence of other realities. This, in turn, would provide a tantalizing glimpse into a far richer and more complex reality than we currently perceive. Neutrino astronomy, too, holds immense potential in unraveling the mysteries of phenomena beyond our universe, including the intriguing concept of alternate or parallel universes. Neutrinos are subatomic particles that, due to their incredibly light and neutral nature, can pass through matter virtually unhindered. This remarkable characteristic makes them excellent messengers, capable of carrying information from distant cosmic events that may be invisible to traditional telescopes. By studying neutrinos, we could uncover evidence of interactions between our universe and others, especially during cataclysmic events such as supernova or black hole collisions. These cosmic occurrences could create anomalies detectable in neutrino patterns and energies, potentially hinting at the influence of other universes. Moreover, theoretical frameworks like string theory suggest the existence of multiple dimensions or parallel universes. Neutrinos, being sensitive to the properties of spacetime, might exhibit behaviors that differ from our expectations based on conventional physics. Their trajectories, energies, and interactions could provide clues to the existence of these extra dimensions, offering a new avenue of exploration. While the study of neutrinos is still in its infancy, the advancement of technology is enabling the creation of increasingly larger and more sensitive detectors across the globe. These developments could soon lead to groundbreaking discoveries. Should unexpected results emerge from neutrino astronomy, they may redefine our understanding of the cosmos and open new pathways in the exploration of multiverse theories, ultimately altering the way we view our place in the universe. In a similar vein, the study of cosmic voids, vast, seemingly empty expanses between the filaments of galaxies, also offers critical insights into the large-scale structure of the universe. Although these voids appear devoid of matter, their study is far from trivial. The very existence of these vast expanses challenges our understanding of gravity and cosmic evolution, making them a focal point for astrophysicists. These voids are not truly empty. They possess unique properties that reflect the gravitational influences of surrounding structures. As researchers analyze the distribution and size of these voids, patterns may emerge that suggest how matter is arranged across the universe. Such patterns could offer valuable clues regarding the distribution of dark energy and dark matter, two unseen forces that govern the expansion of the universe. By examining these cosmic voids, scientists could gain a deeper understanding of how the fabric of the universe behaves, stretching beyond the limits of what we can directly observe. In doing so, they might also uncover evidence that hints at the presence of regions beyond our observable universe, perhaps even offering new perspectives on the nature of reality itself. Moreover, cosmic voids, vast and mysterious expanses of space, may play an unexpected role in helping scientists explore the universe. These immense regions, devoid of matter, can act as natural lenses, bending and amplifying light from distant celestial bodies behind them. This phenomenon, known as gravitational lensing, allows astronomers to peer deeper into the universe, revealing galaxies and cosmic structures that would otherwise remain hidden from view. If there exist cosmic regions beyond the limits of our observable universe, these voids could offer us rare glimpses of light and gravitational effects originating from them. This tantalizing possibility hints at the existence of unobserved structures, expanding the boundaries of our cosmic knowledge. Astrophysicists have long speculated that the properties of cosmic voids might vary across different regions of the universe. Some believe that these differences could be shaped by the forces of cosmic inflation, the rapid expansion that occurred shortly after the Big Bang. Variations in the nature of voids could even signal interactions with distant parts of the universe, areas that remain out of reach from our current observational capabilities. As we continue to refine our understanding of cosmic voids through cutting-edge astronomical surveys and data collection, we might uncover new insights that link our universe to those hidden regions beyond the observable horizon. The discoveries on the horizon could potentially bridge the gap between the known and the unknown, connecting us to cosmic realms that are as yet beyond comprehension. In parallel, the enigmatic cold spots in the cosmic microwave background (CMB) radiation, relics of the early universe, hold further mysteries. These anomalies, regions of the CMB where the temperature is significantly lower than the surrounding areas, are key to understanding the universe's infancy. The CMB is the afterglow of the Big Bang, a faint radiation left over from when the universe was merely 300,000 years old. It provides a snapshot of the universe's earliest moments, offering clues about its composition, the forces at play, and the origins of the structures we observe today. The cold spots in particular stand out as regions that appear less dense, lacking the typical cosmic features found elsewhere in the universe. One compelling theory proposes that these cold spots could be the remnants of cosmic interactions that lie beyond our observable universe. Could they be signatures of events that occurred when our universe collided with another? Some researchers speculate that if such a collision took place, it could have left behind distinct imprints in the CMB, manifesting as these cool regions. This idea fits within the broader framework of multiverse theories, suggesting that our universe may not be the only one. Instead, other universes could be interacting with ours, subtly influencing the cosmic background radiation we detect. While most traditional explanations focus on structures or effects within our universe, the multiverse hypothesis offers an intriguing alternative. If proven, these cold spots could fundamentally alter our understanding of the cosmos, indicating that we are part of a much larger and more complex cosmic web than previously imagined. As scientists continue to analyze data from CMB observations, particularly those gathered by instruments like the Planck satellite, they are piecing together a larger puzzle. These cold spots could be the key to unlocking the deepest secrets of our universe's origins and its connections to other potential realities. With ongoing research, we may soon discover that our universe is not an isolated entity, but rather one of many, coexisting in a vast and intricate multiverse. This realization would not only redefine our understanding of the early universe, but also raise profound questions about the nature of reality itself. Looking ahead, future space-based gravitational wave detectors, like the proposed Laser Interferometer Space Antenna, LISA, offer a promising avenue for further exploration. Gravitational waves, ripples in the fabric of space-time, are produced by some of the most cataclysmic events in the universe, such as the collision of black holes or neutron stars. These waves can reveal valuable insights into the fundamental laws of physics. However, there is also the possibility that they could carry information pointing to other universes. High-energy physics theories, including string theory, propose that our universe might be part of a higher dimensional space, potentially interacting with other universes. If this theory holds true, gravitational waves detected within our universe could carry traces of these additional dimensions, offering an unprecedented opportunity to study phenomena beyond our own reality. Anomalies in the behavior of gravitational waves, such as unusual frequencies or propagation patterns, could signal influences from other universes or dimensions. If such anomalies are observed, they could provide us with a rare observational window into the nature of the multiverse. Gravitational waves, in this context, would not only help us understand the forces shaping our universe, but also open a pathway to exploring the existence of other cosmic realities. The implications of such discoveries would be nothing short of transformative, offering a new frontier in our quest to understand the true nature of the cosmos. Gravitational wave detectors provide a fascinating lens through which scientists can probe the most extreme phenomena in the universe. These detectors, which are sensitive to ripples in space-time caused by cosmic events, allow researchers to examine the collision of objects at unimaginable energies and densities. If our universe interacts with another, such as through the collision of other dimensional objects, the gravitational waves created could bear signatures unlike those produced by typical astrophysical events. By analyzing these waves, scientists search for unique patterns that may suggest interuniversal interactions or even collisions with objects from higher dimensions. As technology advances and more sophisticated space-based gravitational wave observatories are developed, our capacity to detect these elusive waves will grow. The refinement of our data analysis techniques will bring us closer to deciphering the hidden nature of these signals. Gravitational wave exploration represents a thrilling frontier, offering the potential not only to deepen our understanding of the cosmos, but also to reveal evidence of a greater cosmic tapestry, one that may include multiple universes. Every discovery moves us one step closer to answering some of the most profound questions about reality, extending our curiosity far beyond the limits of the observable universe. Similarly, the study of dark energy plays a critical role in the broader field of cosmology. Comprising around 70% of the universe's total energy content, dark energy is responsible for the accelerated expansion of space. Understanding dark energy is key to unlocking deeper mysteries about the cosmos, and it may even provide insights into the existence of other universes. The peculiar behavior and properties of dark energy suggest that it could be connected to mechanisms or interactions that transcend the confines of a single universe. Yet, its fundamental nature remains largely unknown. Several hypotheses seek to explain dark energy's enigmatic role. Some propose that it might be a manifestation of a cosmological constant, while others suggest it could be a dynamic field referred to as quintessence, or perhaps even an effect originating from extra dimensions, as some modern theories of physics propose. If dark energy is indeed linked to higher dimensions or hidden energy fields that coexist with our universe, it could imply that our reality is not as isolated as we once thought. Instead, our universe might be influenced by or even intertwined with other unseen realms. Researchers are also investigating the far-reaching effects of dark energy on the large-scale structure of the cosmos. Anomalies in the distribution and evolution of galaxies might offer the key to understanding its elusive role. If these anomalies deviate from predictions made by current models of observable physics, they could point to interactions with other universes. For instance, if dark energy behaves differently over vast distances or shows irregularities in specific regions of space, it could suggest influences from alternate realities, manifesting either as gravitational effects or variations in the expansion rate of the universe. As we look to the future, continued observations of dark energy through galaxy surveys and cosmic microwave background measurements could reveal unprecedented insights into its true nature. Any discovery that challenges established models of physics could serve as a stepping stone toward contemplating the possibility of a multiverse. In this sense, the ongoing study of dark energy may not only be vital for understanding the forces propelling our universe's evolution, but also for exploring the intricate connections between our reality and other possible universes, connections we are just beginning to comprehend. Meanwhile, advancements in the detection of dark matter particles promise to illuminate even more of the universe's hidden mysteries. Dark matter, which accounts for about 27% of the cosmos, does not emit, absorb, or reflect light, making it incredibly difficult to detect. Yet, its gravitational effects on visible matter, radiation, and the large-scale structure of the universe suggest that it plays a fundamental role in shaping the cosmos. As our technology improves, the ability to detect and understand dark matter could unlock further connections between our universe and other realms, possibly offering another piece to the vast puzzle of existence beyond our observable horizon. However, scientists are relentlessly pushing the boundaries of human understanding, striving to unlock the secrets of dark matter, a mysterious and elusive substance that accounts for a significant portion of the universe's mass, yet remains invisible to our most advanced instruments. Armed with cutting-edge technologies, including underground detectors and large particle colliders, researchers are venturing deeper into the unknown, aiming to uncover the very nature of these hidden particles. One compelling hypothesis suggests that dark matter might not be as intangible as it seems. Instead, it could be composed of particles that interact with gravity and other forces in ways that defy our current understanding of physics. If scientists manage to successfully identify and directly detect these particles, the implications would be profound. It could challenge the very fabric of reality as we know it, indicating that dark matter might not be confined to our universe alone. In fact, certain theories propose that dark matter could be a bridge between universes, perhaps leaking into ours from adjacent dimensions or alternate realities. This idea implies that the gravitational fields we observe could be influenced by forces that originate in realms beyond our own. The very behavior of dark matter, if it deviates from the predictions of conventional physics, could offer a window into these parallel dimensions. For example, unique patterns in how dark matter particles are distributed across space might provide clues to their interactions with unseen forces, lending indirect evidence for the existence of realms far beyond our observable universe. As technological advancements continue at an unprecedented pace, researchers are refining their tools and techniques, developing more sensitive detectors and exploring novel experimental approaches. The ultimate goal? To uncover the true nature of dark matter, and in the process, expand the boundaries of what we know about the universe. Every new discovery in the realm of dark matter brings us closer to reshaping our understanding of fundamental forces, and may provide the theoretical underpinnings that not only explain the cosmos, but also point toward the existence of a vast multiverse. With each revelation, our comprehension of the universe and the many realities that might lie just beyond our reach could be radically transformed. The concept of a living cosmos stretches the limits of our understanding of life, consciousness, and reality itself. In this vision, the universe, or even the multiverse, might possess qualities we typically associate with living systems, but on a scale so vast and intricate that it is almost beyond our grasp. Imagine a cosmic vitality that courses through vast networks of energy, self-regulating processes, and the potential for growth and adaptation. It would be a living entity in ways we cannot yet fully conceive. Picture a multiverse where each individual universe functions like a neuron within a cosmic brain. Here, quantum entanglement might serve as the synapses, connecting these diverse universes into a web of dynamic interaction. Information and energy could flow across these connections, creating patterns of activity so complex that they might appear as thoughts or decisions on a cosmic scale. This cosmic mind could exhibit behaviors that resemble cognition, with different regions of the multiverse specializing in distinct cognitive functions. Some areas of the multiverse could function as memory centers, preserving information about past universal configurations. Others might act as processing hubs, where intricate calculations unfold regarding the evolution of physical laws. In essence, the entire structure could harbor a form of cosmic consciousness, where the collective behavior of countless universes gives birth to a self-aware entity of unfathomable complexity. Reproduction within this living cosmos could unfold through various mechanisms, each offering its own awe-inspiring implications. One possibility suggests universes splitting or budding off from their parent universes, a process akin to cosmic mitosis. This might occur when certain conditions within a universe reach a critical point, such as the density of dark energy surpassing a threshold, or when specialized structures evolve to act as cosmic reproductive organs. As a universe expands and evolves, regions with unique properties could emerge, eventually separating and becoming independent universes. Another tantalizing possibility involves black holes functioning as cosmic wombs, nurturing the development of new universes. Within the extreme conditions at the heart of a black hole, a localized Big Bang could give birth to a fresh universe, one with its own space-time continuum. These newly formed universes would be linked to their parent universes through black holes, potentially allowing for the exchange of information and energy. Over time, this could create a complex web of interconnected universes, united by black hole umbilical cords, each universe feeding off the life force of the others. From this perspective, cosmic natural selection could mirror biological evolution. Universes with properties that encourage the formation of black holes or other universe-generating phenomena would be more likely to give birth to offspring universes. These daughter universes might inherit certain traits from their parent universes, yet also develop slight variations, cosmic mutations, if you will. Over countless iterations, this process could lead to the evolution of universes with increasingly complex and stable properties. The apparent fine-tuning of our own universe might, therefore, not be the result of intelligent design or pure chance, but rather the product of many generations of universal reproduction and selection. Our universe, capable of supporting stable atoms, stars, and galaxies, could simply be the culmination of a long line of increasingly refined cosmic ancestors. But cosmic evolution extends far beyond the boundaries of biological evolution. While the latter is constrained by the laws of physics within our universe, cosmic evolution could involve fundamental shifts in the very fabric of reality itself. As universes mature, they might develop new properties or capabilities, such as the ability to sustain more complex forms of matter or energy. This might give rise to new physical phenomena that are beyond our current comprehension, pushing the boundaries of what we understand about reality. Moreover, cosmic evolution may not be a slow, steady process. Periods of rapid, transformative change could mirror what we know as punctuated equilibrium in biological evolution. These cosmic revolutions could be sparked by the interactions between universes, the influence of higher dimensional spaces, or the emergence of new fundamental forces. During such times, entirely new types of universes might arise, radically different from their predecessors. These fresh forms would then undergo their own evolutionary processes, potentially creating an ever-expanding diversity of universal types. One fascinating idea in this context is the concept of a universe's metabolism, an intricate system of energy and information exchange between universes. In this vast cosmic economy, the waste products of one universe might serve as vital resources for another, forming a complex network of interdependence across the multiverse. For example, when a universe nears the end of its life cycle, approaching heat death or a big crunch, it might release vast quantities of energy or information. This cosmic exhaust could then be harvested by younger, expanding universes, fueling their growth and complexity. Some universes might specialize in energy production, acting as cosmic power plants that supply the neighboring universes with the fuel needed to sustain their laws of physics. Other universes might focus on information processing, serving as cosmic computers that tackle complex problems or store immense amounts of data. These information-centric universes could function as memory banks or processing centers for the entire multiverse, playing a crucial role in its evolution and self-regulation. A truly extraordinary possibility lies in the idea of symbiosis between universes. Just as organisms in an ecosystem form complex, interdependent relationships, universes within the multiverse could engage in a delicate dance of mutual benefit. Certain universes might act as cosmic incubators, offering ideal conditions for the formation and growth of new universes. These nursery universes could possess physical laws fine-tuned for the rapid development of new cosmic structures, serving as the breeding grounds for the next generation of universes. Meanwhile, other universes might help maintain the stability of the multiverse as a whole, ensuring the interconnected web of existence continues to thrive. In this grand cosmic ecosystem, universes are not isolated entities, but are part of a larger, dynamic process that unfolds on scales we can hardly begin to imagine. Each universe contributes to the intricate balance, ensuring that the evolution of the cosmos, on both a grand and microscopic scale, continues in a harmonious and complex dance of interdependence. In this living cosmos, life and consciousness stretch far beyond the limits of biological understanding. The entire multiverse might be an interconnected, self-regulating system, constantly evolving, adapting, and creating new forms of existence. This is a cosmos not just of stars and galaxies, but of thought, energy, and life, a universe of infinite potential waiting to be explored. In the boundless expanse of the multiverse, cosmic anchors may exist, universes with unshakably stable physical laws, acting as the bedrock upon which other, more dynamic universes can form and evolve. These stable realms serve as the necessary framework that supports the development of others, where change is a constant and innovation thrives. The delicate interaction between these stable universes and their dynamic counterparts could create a balance, a harmony that allows for both consistency and transformation across the wider multiverse. Some universes, in this vast and intricate structure, might form symbiotic relationships. These pairs or groups of universes work together, each fulfilling an essential role for the others. For example, one universe might specialize in the production of complex matter, while another focuses on generating exotic forms of energy. The partnership between such universes allows them to achieve extraordinary levels of complexity and stability that would be unattainable in isolation. Over time, these symbiotic bonds could lead to the emergence of universe clusters, perhaps even superorganisms, vast, interconnected entities composed of many universes, each playing a crucial role in the larger whole. Just as ecosystems on Earth have built-in defense mechanisms, universes may evolve cosmic immune systems to shield themselves from various existential threats. These dangers could range from internal instability and the collapse of physical laws to the intrusion of foreign universes, or even the degradation of their very structure. Universes with robust defenses would naturally be more likely to survive and replicate, passing on their resilient traits to the next generation of cosmic forms. One of the most fascinating aspects of these cosmic immune systems is their potential for repairing and safeguarding space-time itself. Universes might possess the ability to mend tears in the fabric of reality, perhaps by generating exotic matter with negative energy density. Others could develop sophisticated mechanisms to stabilize fluctuations in vacuum energy, preventing the destructive forces that could trigger their expansion or collapse. The most advanced systems might even be capable of repelling invasive matter or energy from other universes, preserving the integrity of their own physical laws and structures. Over countless eons, these immune systems might evolve, potentially sparking a cosmic arms race. Universes might develop offensive capabilities, expanding into neighboring territories, or siphoning resources from one another. In response, defensive capabilities would also advance, leading to the formation of highly secure, nearly impenetrable universes, fortresses against external threats. In this evolving cosmic landscape, universes might also specialize in fulfilling distinct ecological niches within the broader multiverse. Such specialization could foster a breathtaking variety of universal types, each fine-tuned for its role. For example, some universes might be optimized to produce black holes, acting as cosmic engines that drive the creation of new universes. These black hole factories would boast physical laws designed to facilitate the rapid formation of massive stars, triggering frequent supernova explosions and generating vast numbers of black holes. Meanwhile, other universes could become sanctuaries for life. With physical constants tuned to perfection, they would support the formation of stable planetary systems and the emergence of diverse life forms, perhaps even life unlike anything we can imagine. These life-bearing universes would become biodiversity hotspots in the cosmic ecosystem, ensuring the richness and diversity of the multiverse. Other universes might evolve to become cosmic computers, excelling at information processing on a grand scale. With laws of physics that allow for the efficient manipulation and storage of information, these universes could play a crucial role in solving complex problems that affect the entire multiverse. They could also act as repositories, preserving knowledge from dying or collapsing universes, safeguarding the collective memory of the cosmos. Power-generating universes might also play a pivotal role in sustaining the cosmic ecosystem. These universes, filled with high levels of vacuum energy or periodic high-energy events like gamma-ray bursts, would serve as energy sources for their neighbors. This surplus energy could fuel the operations of information-centric universes, which in turn might influence the evolution of life-bearing realms. Thus, a complex web of cause and effect would stretch across the multiverse, where the energy produced in one universe could spark the development of life in another. Just as biodiversity is essential for the resilience and adaptability of life on Earth, cosmic biodiversity could ensure the survival and ongoing evolution of the multiverse itself. The diversity of universal types, each with its own unique properties and capabilities, would buffer the system against large-scale disturbances. Some universes might operate under entirely different sets of physical laws, or perhaps exist with varying numbers of spatial and temporal dimensions, creating entirely alien forms of matter and energy. This diversity would drive innovation and complexity at an unimaginable scale. Furthermore, universes with compatible physical laws might share knowledge, ideas in the form of universal structures or successful physical laws. This cosmic cross-pollination could lead to rapid evolutionary leaps across the multiverse, spreading beneficial traits over vast distances and accelerating the overall evolution of the cosmos. In the end, the multiverse may be a place of unimaginable variety, where stability and change coexist, where symbiosis and competition shape the course of cosmic evolution. Each universe, with its unique role, contributes to the greater whole, a cosmic ecosystem of staggering complexity and beauty. Moreover, cosmic biodiversity might hold the key to safeguarding the multiverse from existential threats, preserving its longevity in the face of catastrophic events. Imagine a scenario where a particular type of universe faces a cataclysm. Perhaps an unknown cosmic danger endangers its very existence. In such an instance, the sheer diversity of alternative forms within the multiverse would act as a safeguard, ensuring that even if one universe is destroyed, the broader cosmic structure continues to thrive and evolve. This resilience is not just theoretical, but might be absolutely crucial when faced with hypothetical existential risks, like vacuum decay or even the collision of brains in certain string theory models. In this context, cosmic biodiversity could act as a protective buffer, preserving the multiverse as a whole. The principles of adaptation and fitness, often applied to the biological world, take on new dimensions when applied to the cosmic scale. Universes themselves could undergo a form of evolution, shaped by their ability to support complex phenomena like consciousness, or to store and process vast amounts of information. The very concept of fitness at a universal level could involve factors far beyond our current comprehension. Consider, for instance, the ability of a universe to maintain stable physical laws or to resist cosmic catastrophes. These qualities might not just determine the survival of a universe, but could also influence its potential to generate new universes in a continual cycle of cosmic creation. Universes exhibiting greater fitness, those that support complexity, produce black holes, or endure over the ages, may have a higher likelihood of persisting through cosmic time, evolving into increasingly complex and stable forms. This process might mirror, in some ways, the evolutionary drive we see in biological life, but on a grander, far more abstract scale. However, the evolution of universes would differ dramatically from the biological evolution we are familiar with. The timescales involved would be inconceivably vast, with changes unfolding over billions or even trillions of years. The forces driving this cosmic evolution would operate at levels beyond our current understanding. Instead of natural selection acting on genetic material, selection might occur through shifts in the fundamental physical constants or through variations in the very fabric of space-time itself. These universes could be subject to pressures originating from the interactions with other universes, from the mysterious influence of higher dimensional spaces, or even from the intervention of advanced cosmic civilizations, capable of engineering entire universes. As universes compete, adapt, and evolve in this vast cosmic arena, the multiverse might itself move toward greater complexity, creating new structures or phenomena beyond our current understanding. Phenomena that might transcend even the concepts of space, time, and physical laws. In this grand cosmic drama, our own universe could be seen as a single player in an eternal cycle of creation, destruction, and renewal. The principles of cosmic ecology, if they indeed operate at these unimaginable scales, might offer a framework to understand our place in a reality far grander and more intricate than we ever imagined. It suggests that our universe is just one node in a much larger, infinitely intricate system, one that has been evolving in ways we are only beginning to glimpse. This leads us to the concept of infinity, which plays a profound role in our discussions about multiple universes and the very nature of existence. In traditional cosmology, the universe is often treated as a finite entity, confined by time and space. However, when we introduce the idea of infinity, the possibilities expand exponentially. An infinite universe could mean that every conceivable configuration of matter and energy exists somewhere within that boundless expanse. Now consider the multiverse, an infinite collection of parallel universes, each one representing a different reality, each born from different possibilities. The idea that each decision or event could spawn a new universe means that infinity grants us the existence of an endless array of outcomes, each one occupying its own distinct universe. This means that within this infinite multiverse, every conceivable possibility, every choice ever made, might play out in its own unique reality, creating an unending tapestry of interconnected and diverging universes. These alternate realities could intersect with ours at times, or they could exist entirely apart, in a constant dance of divergence and convergence. The idea of an infinite, multiverse-spanning reality challenges the very boundaries of our understanding and perception of existence. It suggests that the universe is not a singular, fixed entity, but rather part of a boundless, evolving cosmos that contains within it every possibility, an endless reality where the potential for new discoveries, new universes, and new forms of life is only limited by the imagination of the cosmos itself. Moreover, mathematical models that incorporate infinity offer an intriguing possibility. They suggest that the laws of physics might not be the same across different universes. Instead, they could vary, with different constants or fundamental forces creating entirely distinct environments. These other realms could host conditions where life, space, and time behave in ways that we, in our universe, may be unable to even fathom. The implications of this notion are nothing short of staggering, as it challenges the very core of our understanding of reality and the nature of existence itself. As scientists push the boundaries of their exploratory frameworks, especially through concepts like string theory and cosmic inflation, discussions about infinity and the multiverse are gaining momentum. These theories are not just intellectual exercises. They aim to unify our understanding of cosmic phenomena. At their heart, they seek answers to some of the most profound questions humanity has ever posed, including the nature of reality, the origins of existence, and the fundamental structure of space-time. Infinity, in this context, becomes a pivotal foundation for thinking about how many universes might exist and what the interactions between them could entail. The potential existence of a true multiverse brings profound and multifaceted implications for the very fabric of reality and our place within it. If the multiverse is indeed real, it suggests that our own universe, our observer universe, is just one of countless others, each with its own unique set of physical laws, constants, and dimensions. This idea raises essential philosophical questions about existence itself, challenging the distinctions between what is real and what might be only a small fragment of a much larger, more complex cosmic tapestry. One of the most compelling consequences of the multiverse concept is the idea that it opens up an almost infinite number of possibilities. If every conceivable outcome has the potential to occur in some universe, it means that every choice, every event, and every iteration of reality could exist somewhere within this vast multiverse. Imagine the consequences for human decisions. A choice made today might create an alternate universe in which a completely different path was taken. This vast diversity of experiences across infinite universes offers a richer, more layered understanding of existence. It hints at the possibility that our lives and the choices we make may have counterparts unfolding in parallel realities. Furthermore, the concept of a true multiverse challenges the notion of fine-tuning, the idea that our universe is uniquely designed with the perfect conditions for life. If there are infinite universes, each with varying parameters, some of them would certainly be inhospitable to life. In this context, our universe might simply be one where the conditions happen to align just right, making life possible. This revelation raises profound questions about the uniqueness of our own reality. Is our universe an extraordinary fluke, or is life more common than we once thought, spread across countless other realms? In turn, this idea compels us to reevaluate our assumptions about intelligent civilizations. If other universes harbor life, how likely is it that we are not alone in the cosmos? The idea that the multiverse might not only expand our understanding of what constitutes reality, but also alter the likelihood of encountering other advanced forms of intelligence, adds yet another layer of awe and mystery to our place in the grand cosmic narrative. The concept of the multiverse opens a profound space for exploring the deepest corners of reality, philosophy, and even spirituality. If multiple universes indeed exist, they challenge the very foundation of our understanding of existence. At the intersection of science, philosophy, and metaphysics, the multiverse forces us to reconsider the nature of what we call reality. The idea that our universe could be just one of countless others invites an entirely new framework for thinking about existence, not as a singular event, but as a complex, layered phenomenon, unfolding in ways we may not yet fully comprehend. What does it mean to be alive and aware in a universe that may be but one of an infinite array of realities? This very question ignites a vast philosophical exploration into the core of existence. The multiverse suggests that existence itself is not a fixed, singular event, but an ongoing, evolving process of infinite possibility. Every choice, every decision, every thought could lead to a divergent path, potentially creating a new universe where alternate versions of reality emerge. This expands the scope of human exploration far beyond the material world and invites us to reflect on deeper metaphysical concepts. At the heart of the multiverse theory lies an intriguing challenge to the idea of uniqueness and identity. If the multiverse is true, then it proposes that every possible version of ourselves, every potential choice, every alternate life experience exists in some parallel universe. This raises fundamental questions about the nature of identity. What does it mean to be unique when countless versions of us exist across an infinite number of realms? If our choices and actions can give rise to separate realities, then the concept of a singular identity, what we think of as me, becomes fluid and multifaceted, shaped by countless paths that might have diverged from one another in the vast expanse of the multiverse. The idea that there could be infinite versions of each individual, each experiencing life along different trajectories based on alternative decisions or circumstances, is both fascinating and deeply disorienting. Imagine for a moment that each decision you make, whether it's something as small as choosing what to eat for breakfast or as monumental as deciding a career path, creates a new universe. In this parallel world, a different version of you has taken a different route, living a life completely distinct from yours. This notion strips away the certainty of identity and offers a view of selfhood as a vast mosaic, where each you is shaped by divergent decisions, experiences, and outcomes. Such a framework encourages us to rethink what it means to truly know oneself. If you are only one version of countless others, can you ever truly understand the essence of who you are? Is it possible to know yourself when your identity is spread across infinite realities, each shaped by its own unique set of circumstances? Identity, then, is not singular. It is a tapestry woven from the threads of myriad experiences, all of which converge in the web of the multiverse. Furthermore, this raises philosophical inquiries into the nature of selfhood and the very fabric of human experience. What does it mean to be me when there are infinite versions of me? If each version of you exists in a separate universe, does that mean there is no fixed you at all, but rather a shared concept of self that stretches across multiple realms? Could it be that the essence of identity is not confined to our individual experiences in this one reality, but is instead an ever-evolving collective phenomenon that transcends the boundaries of one universe? The implications of this are not just personal, they extend to the collective human experience. The multiverse theory suggests that our universe, our history, our civilization, may not be as unique or as isolated as we believe. If entire civilizations, histories, and events exist simultaneously across multiple realities, then the singular significance of any one discovery or accomplishment could diminish in light of the broader multiverse context. What is the value of an achievement, a creation, or a cultural milestone when similar versions exist in other realms? This prompts us to reconsider our concept of greatness and challenges us to think of human accomplishments as part of a much larger, interconnected web of infinite realities, each containing its own variations of our collective history. This shift in perspective challenges our traditional views on what it means to be special or unique. If all things exist in some form or another across infinite universes, then the meaning we attach to individual identity and accomplishment may be more fluid and complex than we ever imagined. Instead of seeing ourselves as isolated beings, we might begin to view our existence as part of a larger, interconnected network, a collective journey spanning across an infinite number of realities. Perhaps most significantly, the concept of the multiverse raises deep questions about consciousness and the nature of self-awareness. If countless versions of ourselves exist in parallel universes, how do we define consciousness? Is consciousness something that is inherently tied to our specific reality, or does it manifest us across multiple realms? What does it mean to be truly conscious if there are infinite versions of our awareness scattered throughout an endless array of universes? This suggests that consciousness may not be as singular or isolated as we once believed. It may not reside only in this universe, but could extend across multiple planes of existence, each version of ourselves experiencing the world in a distinct yet interconnected way. As we venture further into the implications of the multiverse, we confront the concept of free will. If every choice we make could lead to the creation of a new universe, does this mean that the paths we take are not only possible, but are actually realized in parallel realities? The notion of infinite outcomes creates a new layer of complexity in how we understand the consequences of our actions. What does it mean to choose if every decision we make could spawn multiple parallel versions of ourselves living out different destinies? The multiverse offers an entirely new framework for considering not only who we are, but also the infinite paths we may take, leading to a deeper understanding of our place in the cosmos. In the end, the multiverse invites us to reimagine not just the physical universe, but also the very nature of existence, identity, consciousness, and choice. It challenges us to consider that what we think of as reality might be just one layer of a far more intricate and expansive cosmos, filled with infinite possibilities and versions of ourselves. And as we contemplate this, we may find that our understanding of who we are and what it means to be alive will never again be the same. Moreover, the ethical considerations of a multiverse, populated with infinite versions of ourselves, present an intriguing complexity. If every action we take spawns outcomes in separate universes, how does this influence our sense of responsibility for our choices? Philosophically, this raises profound questions about the ethical weight of our decisions. In a universe where we might acknowledge not just the impact of our actions within our specific realm, but how they reverberate across countless others, we are confronted with an ethical conundrum. Do we then carry a heightened sense of personal accountability, knowing that our choices could ripple through infinite realities? Or does this realization lead to a form of existential paralysis, a paralyzing uncertainty about the significance of any single decision when faced with so many possible iterations? As we contemplate the existence of infinite versions of ourselves, each leading lives of varying moral character, we are also forced to reflect on the universality of human values. If there are versions of ourselves living lives with differing ethical standards, what does that say about the universality of moral principles? This can ignite profound reflections on what it truly means to live a good life. The existence of multiple universes with multiple versions of us challenges the notion of a singular universal moral framework. It asks us, do moral principles shift from one universe to another? Can a single set of values ever be adequate in a multiversal context? This complexity compels us to critically examine fundamental concepts like identity, consciousness, morality, and free will, especially within the vast, uncharted context of existence itself. As the idea of the multiverse weaves its way into age-old debates, it brings fresh perspectives to the long-standing battle between determinism and free will, prompting us to question established assumptions. Determinism asserts that every event, including human actions and decisions, is the inevitable result of preceding causes governed by natural laws. In a deterministic universe, it seems to imply that the future is predestined, shaped by influences outside of our control. But when the concept of a multiverse is introduced, where every possible outcome of every decision exists in a separate reality, the lines between determinism and free will blur. Imagine, for instance, someone facing a pivotal decision, such as choosing between two career paths. According to the multiverse theory, their choice would result in the creation of two distinct universes, one where they pursue one career and another where they embark on the other. In this framework, the multiverse allows both determinism and free will to coexist. Each choice an individual makes represents an act of free will, yet those choices also lead to deterministic outcomes, with multiple universes branching off to reflect those choices. But this introduces further complexities. If we accept the existence of a multiverse, then questions about causation and personal choice become more complicated. From a deterministic viewpoint, what determines the choices made in each universe? Is there an underlying randomness, or are other factors shaping the decisions within each reality? This dilemma further complicates our understanding of personal agency and accountability. If every decision spawns infinite paths and alternate realities, what does it even mean to say that an individual has truly made a choice? Does an individual's decision matter if it simply leads to the creation of countless versions of themselves across different universes? Rather than opposing determinism, the multiverse theory suggests a more nuanced interpretation of free will. Individuals might be seen as navigating a complex web of choices, where each decision not only shapes their immediate reality, but also contributes to a broader, richer tapestry of possibilities in the multiverse. In this light, the interplay between identity, decision-making, and personal agency becomes more intricate as the philosophical implications of living in a reality filled with infinite potential outcomes expand. It compels us to reconsider how we perceive our actions in a world teeming with countless variations of existence. Additionally, the multiverse concept raises profound questions about creation itself. Traditional religious and philosophical narratives often center around the idea of a singular universe intentionally created by a divine force. However, in a multiverse, where endless universes might emerge from a variety of mechanisms, the nature of creation becomes far more complex. If countless universes exist, each governed by different physical laws and conditions, it challenges our conventional notions of a creator. Is this creator responsible for the birth of a single universe, or do they oversee a vast, interconnected multiverse? If the multiverse arose from natural processes such as quantum fluctuations or cosmic inflation, could it suggest that the creator's role, if any, was less about crafting a singular universe and more about setting the initial conditions that allowed multiple realities to emerge? In such a view, the creator would not be a hands-on architect of a single reality, but rather a facilitator of the natural laws that give rise to an infinite spectrum of universes. These considerations push us to rethink our deepest assumptions about creation, existence, and the nature of divinity itself. As we grapple with the possibility of multiple, infinite versions of reality, we are invited into a profound exploration of the universe's origins and the role that a creator might play in the grand, multifaceted scheme of existence. The existence of infinite universes, each with its own unique characteristics, presents a compelling shift in how we might understand the divine purpose. In a multiverse framework, the sheer variety of environments and forms of life across these universes could reflect a creator's desire for exploration, diversity, and a broader expression of existence. Such a perspective would invite the possibility that individuality and freedom within each universe are expressions of a creator's boundless creativity, designed to unfold in diverse ways across infinite realms. However, the very concept of a multiverse raises questions for traditional theological views that emphasize a personal, interventionist deity. If universes can arise spontaneously through physical processes, it challenges the necessity of a creator in the conventional sense. This leads to profound philosophical questions. If we are merely one of countless possible realities, what significance do our actions and existence hold in this broader cosmic context? It beckons a reevaluation of purpose, urging us to explore meaning beyond the limitations of a single universe. Ultimately, the idea of a multiverse sparks various interpretations of creation, offering fertile ground for enriching discussions at the crossroads of science, philosophy, and personal belief. It encourages a reimagining of spiritual frameworks and our understanding of reality, illuminating the potential for diverse and evolving narratives that intersect at the complex junction of all these realms. The existence of multiple universes could dramatically shift our perceptions of cosmic evolution and the complexity of the cosmos itself. If the multiverse is real, it implies that our universe is merely one of many, each evolving under distinct conditions and governed by different laws of physics. This idea opens exciting new avenues for exploration, particularly in understanding how complexity arises, not just in our universe, but across all potential realities. One of the most striking implications of this view is the possibility that the fundamental constants governing our universe are specifically tuned to allow for the emergence of complex structures, such as galaxies, stars, and life itself. In a multiverse scenario, however, each universe may have different physical constants. This could lead to radically different evolutionary pathways. Some universes may evolve into realms teeming with life, while others remain barren and uninhabitable. The variability across these universes suggests that complexity is not a given outcome, but one of many possibilities, contingent on the specific conditions of each universe. Furthermore, examining cosmic evolution within a multiverse context allows for a broader understanding of phenomena like cosmic inflation, dark energy, and the formation of structures. For example, if inflation can occur across multiple universes, it could explain how different regions of space evolve independently, each with its own unique cosmic history. This could provide insight into the vast variations in galaxy formation and development seen throughout the observable universe. Our own universe, in this context, is simply one realization of cosmic evolution within an infinite tapestry of others. The multiverse model also calls into question the principles of natural selection and emergence. In a reality where numerous universes exist, we can hypothesize that complexity might not arise solely from adaptation to specific environments, but could be shaped by entirely different evolutionary pressures in parallel realities. Such a framework could unveil new dynamics behind design, organization, and complexity, encouraging scientists to develop new theoretical models to account for the variations found across these diverse realms. Ultimately, the possibility of multiple universes enriches our understanding of cosmic evolution. By examining how different laws of physics and initial conditions play out across countless realities, we can gain deeper insights into the emergence of complexity and the rich diversity of existence. This could lead to a rethinking of not just the mechanisms behind cosmic formation, but also our place within the vastness of the cosmos. In a multiverse, the ethical implications of our decisions and their consequences become profoundly more complex. In a reality where every possible choice spawns a branching universe with its own unique outcomes, the understanding of moral responsibility becomes layered and multifaceted. In traditional ethical frameworks, we typically link responsibility to the consequences of specific actions. If someone takes an action that leads to a negative result, they are held accountable for that decision. Yet, in the multiverse, where every decision gives rise to countless alternate outcomes, this accountability becomes far more intricate and uncertain. As we delve into the potential ethical landscapes of the multiverse, we are forced to reconsider what it means to be responsible, how to understand morality, and what it truly means to make a meaningful choice. In such a vast, branching reality, the lines between right and wrong, responsibility and consequence, become increasingly blurred. Our sense of duty, accountability, and even purpose may shift in ways we have yet to fully comprehend. The multiverse challenges us to confront not just the nature of the cosmos, but also the core of human experience, morality, and the essence of our decisions. However, in a multiverse, the choices an individual makes could lead to an infinite array of possibilities, where each decision unfolds into multiple parallel realities. This idea raises profound questions about the ethics of decision-making. Imagine, for a moment, a scenario in which one person's choice results in harm in one universe, yet in others it might lead to entirely positive outcomes. Does this suggest that their moral responsibility becomes diluted or dispersed across these countless realities? In such a world, the traditional notion that we are solely accountable for our actions is called into question, opening up the possibility of a more collective and interconnected understanding of morality that spans beyond any single existence. In this scenario, individuals might experience what could be described as existential paralysis, If every decision imaginable is realized in one universe or another, does it render the choices we make here and now meaningless? This realization might lead to a sense of ambiguity regarding the significance of ethical decision-making. If someone believes their actions will simply be replicated in countless other universes, they may begin to wonder whether their moral choices matter at all. This, in turn, could lead to ethical nihilism, the belief that striving for good is ultimately futile. However, this awareness could have the opposite effect, sparking a profound sense of compassion and interconnectedness. By recognizing that our actions ripple through a web of realities, individuals might come to see that their choices transcend a single thread of existence, extending into a broader, interconnected whole. The multiverse dilemma also stirs a complex discussion around empathy. If we accept that every decision we make branches out into alternate realities, where versions of ourselves experience different outcomes, this might compel us to cultivate a deeper empathy for others. Understanding that our actions have far-reaching consequences, not just within the confines of our own universe, but across multiple interconnected realities, could inspire a shift in how we approach ethical decision-making. Each choice becomes a thread in a vast, intricate web, and the weight of that responsibility could drive individuals to make decisions that contribute positively to the collective experience of sentient beings across the infinite reaches of the multiverse. Ultimately, the ethical implications of a multiverse challenge us with some of the most fundamental questions about existence. What does it mean to be responsible for our choices? What is the significance of a single decision if every possible variation of it exists somewhere else? And how do we reconcile our personal moral frameworks with a reality that may contain endless possibilities and outcomes? Engaging with these concepts not only pushes us to reflect more deeply on our personal ethics, but also forces us to rethink the complexities of morality in a world where multiple universes and countless outcomes exist side by side. Beyond the realm of ethics, the concept of the multiverse fundamentally reshapes our understanding of causality and the nature of cause and effect relationships. In classical physics, causality is typically viewed as a linear progression. A single cause leads to a specific, predictable effect. This framework provides a simple, straightforward way to understand how events unfold in time and space. However, in a multiverse, where every possible outcome of a decision or event plays out in parallel realities, the linear connection between cause and effect becomes far more intricate. Each choice, each event, becomes a branching point in the fabric of reality. Rather than a singular, unidirectional flow, causality turns into a vast, branching tree. Every cause can sprout multiple divergent effects, each giving rise to its own timeline or universe. This challenges our traditional understanding of causality, where one action can lead to one outcome. In a multiverse, the same cause can produce wildly different results depending on which branch of the tree you are observing. Moreover, the existence of multiple outcomes in different universes raises fundamental questions about the very nature of causation. If every possible scenario unfolds somewhere in the multiverse, what does it even mean for one event to cause another? For instance, if someone makes a decision that leads to both success and failure in different universes, can we still attribute a single effect to a specific cause? This complexity challenges the very core of how we think about cause and effect in our universe. In a reality where multiple outcomes coexist, can we reliably predict the results of our actions when the same action could unfold in entirely different ways in parallel realities? In essence, the multiverse forces us to reconsider causality itself, not as a straightforward chain of events, but as an intricate web of interconnected possibilities, where every choice and every action might have an infinite number of consequences. This profound shift in perspective may challenge everything we thought we knew about the nature of time, space, and responsibility, urging us to think beyond the boundaries of our own existence and explore the vast, mysterious web of realities that stretch out before us. The concept of causality becomes intricately entangled with the ideas of chance and randomness within the vast expanse of the multiverse. Here, events that unfold might appear determined by seemingly random fluctuations, with outcomes varying dramatically across the many versions of reality. This notion sparks profound philosophical inquiries into the nature of determinism, free will, and the role of chance in the evolution of countless universes. What we often perceive as random, it seems, may in fact be nothing more than the visible manifestation of an infinite variety contained within the multiverse. In this framework, each potential outcome holds its own validity, shaped by the unique context of its respective universe. The idea of the multiverse forces us to rethink causality and the traditional linear understanding of cause and effect. We're drawn into a deeper consideration of the complex interactions that bind realities together, suggesting that every action, every choice, ripples across multiple dimensions and resonates through the vast interwoven expanse of existence. This broadened perspective urges us to explore the myriad possibilities that define our universe, thus nudging us toward a more profound investigation into how our decisions and actions not only shape our personal lives, but also influence the grander tapestry of existence across infinite realms. In such a framework, the multiverse holds transformative implications for the very concepts of cosmic significance and purpose. It compels us to reconsider what it truly means to find meaning in a universe or series of universes where an endless number of realities coexist. For centuries, philosophical and religious traditions have held that our universe is one of a kind, uniquely purposeful, often tying human existence to a grand design or overarching narrative. However, the existence of the multiverse offers a radically different lens through which to view significance and purpose. If our universe is merely one among countless others, each with its own set of physical laws and distinct histories, then the very idea of a singular cosmic purpose becomes far more complex, even potentially diluted. When we place the events and milestones of our universe against the backdrop of innumerable others, each with its own narrative, what once seemed unique and extraordinary may now appear less so. This raises difficult yet essential questions about the true nature of human experience and the role of cosmic events. Are our endeavors, our triumphs, and our struggles any less meaningful because they may be mirrored in other universes? Alternatively, one could argue that the very diversity of existence enhances the significance of these events, imbuing them with new meaning as they form part of a much larger, ever-expanding narrative across realities. Furthermore, this perspective challenges traditional notions of meaning itself. If every possible outcome, no matter how improbable, finds its place in the multiverse, then significance may no longer be confined to a singular path or timeline. Instead, it could be viewed as a vast and interconnected web, where each universe contributes in its own unique way to the overarching narrative of existence. This understanding of the multiverse encourages a broader, more inclusive concept of cosmic significance, where meaning emerges not just from our individual lives, but from the complex interweaving of countless realities, each offering its own story and its own perspective. The multiverse, then, also opens the door to a more fluid and personalized view of purpose. In a realm where endless possibilities exist, individuals might discover personal meaning through their own choices, experiences, and relationships within the specific context of their universe. This gives rise to a profoundly empowering notion. Purpose is not something imposed upon us from an external source, but is something we have the power to define for ourselves. In this vast, ever-shifting landscape, meaning is a product of personal agency, an individual's capacity to create significance in the face of infinite alternatives. Thus, the multiverse invites us to step beyond traditional confines, to consider a broader, more dynamic sense of purpose, one that is as diverse as the realities in which we exist. In this framework, each choice we make, no matter how small, contributes to the larger narrative of existence, and influencing not only our personal journey, but the vast interconnected web of the cosmos itself. The multiverse, at its core, challenges us to confront fundamental questions about the nature of existence, meaning, and purpose. It invites a deeper, critical reflection on the concepts that govern our understanding of reality, expanding our sense of significance beyond the confines of a single universe. This grand expanse of infinite possibilities calls us to reconsider meaning within the context of a vast, interconnected web of realities, each offering unique pathways for personal interpretation and agency. As we explore the multiverse, we find ourselves standing at the intersection of science and philosophy, where the search for purpose becomes an ever-expanding inquiry. In this grand framework, our individual experiences are not isolated, but are part of a greater cosmic whole, one that suggests the possibility of interconnectedness across all realities. The multiverse, then, is not just a speculative notion, but a concept that invites rich philosophical discourse, urging us to probe into what it truly means to seek purpose in a universe teeming with boundless opportunities. At the heart of this exploration lies the concept of a living cosmos, a dynamic, self-organizing entity. But this doesn't imply consciousness as we typically understand it. Instead, it suggests that the cosmos, or the multiverse as a whole, exhibits behaviors that echo those of living systems. These are not acts of intentionality, but rather complex, evolving processes that allow for the emergence and adaptation of cosmic structures over time. In this view, entire universes might act like cells within a larger cosmic organism, each one fulfilling a critical role to maintain balance within the system. But how do these universes evolve? How do they communicate with one another, if at all? In the vast unseen realms beyond our observable universe, these questions become central. Perhaps universes exchange energy or information through quantum entanglement or through higher dimensional connections that we can barely begin to comprehend. This interconnectedness forms a kind of cosmic neural network where signals propagate across the multiverse, subtly influencing the development and behavior of individual realities. One could imagine these universes as constantly evolving and, in some cases, even reproducing. Just as cells divide, so too might universes, splitting off from one another, each born out of the energy density or critical expansion points of their parent. The idea of cosmic mitosis posits that universes reach certain thresholds, causing them to split into new entities. These divisions could be triggered by shifts in the density of dark energy or by the formation of highly specialized cosmic structures. In this way, the birth of new universes mirrors biological processes on an unimaginably grand scale. Even more mind-bending is the notion that black holes could serve as the wombs for new universes. As matter collapses into singularities, it may punch through the very fabric of space-time, emerging as new realms in what we could understand as a cosmic Big Bang. This idea suggests that the multiverse is not a static entity, but an ever-changing and evolving system, where each universe could potentially give rise to an entire lineage of new realities. This process of cosmic natural selection, much like biological evolution, introduces a powerful concept. Universes evolve over time. Universes with certain characteristics, such as the ability to form stable black holes or achieve specific energy states, might be more likely to reproduce. Over cosmic timescales, this could lead to a multiverse populated with universes that are increasingly fine-tuned for complexity, stability, and possibly the emergence of life. Furthermore, cosmic natural selection may offer an explanation for the apparent fine-tuning of our own universe. The physical laws that govern our existence could be the result of countless iterations and refinements, a long process of cosmic trial and error. Just as life evolves through the accumulation of beneficial traits, so too might universes adapt and evolve, constantly refining their physical laws through interactions with one another or internal changes. The laws of physics themselves could undergo mutations, shifting over time as universes adapt to the pressures of their own existence. Some universes may thrive by developing more stable life-supporting laws, while others could succumb to entropy or collapse. But those that do survive and persist could spawn offspring universes, passing on their successes or failures. This dynamic process might resemble a cosmic metabolism, where universes exchange energy or information to maintain a kind of equilibrium. These exchanges could take place through quantum entanglement, higher dimensional connections, or the creation of baby universes. Some universes might specialize in energy production, while others focus on information processing, creating a balanced, diverse cosmic ecosystem. In this system, the waste products of one universe could become vital resources for another. The entropy or information loss in one reality could fuel the creation or complexity of another, leading to a kind of cosmic symbiosis. Some universes might act as incubators, creating ideal conditions for the birth of new realities, while others could serve as stabilizers, maintaining the overall structure of the multiverse. In time, this interconnectedness could evolve into more sophisticated forms of protection. Universes may develop their own immune systems to shield themselves from collapse or interference. These self-regulating mechanisms might allow universes to stabilize physical constants or even neutralize harmful fluctuations in space-time. Universes that evolve these robust defenses would have a better chance of survival, ensuring their place within the ever-expanding multiverse. This cosmic arms race could lead to the emergence of universes that specialize in certain roles, much like species adapting to ecological niches on Earth. Some universes might excel at creating complex structures, while others might specialize in energy production or information processing. These variations could drive the overall evolution of the multiverse, pushing the boundaries of what is possible in terms of complexity and order. A rich cosmic biodiversity might emerge from this dynamic, with each type of universe contributing to the resilience and evolution of the larger system. Just as biodiversity ensures the stability of ecosystems on Earth, a diverse array of universes could provide the foundation for the long-term survival of the multiverse itself. This biodiversity might take countless forms, from universes that operate under entirely different physical laws to those that exist in dimensions we cannot perceive. In this cosmic ecosystem, fitness, survival of the most adaptable, applies not only to life forms but to entire universes. Those that are better suited to their environments, capable of sustaining complexity or producing black holes, may be more likely to persist and reproduce. As the multiverse continues to evolve, universes might grow more sophisticated, developing new properties, capabilities, or even entirely new forms of existence. Ultimately, the multiverse is not just an abstract concept. It is a dynamic, living system, constantly evolving and adapting. As universes compete, cooperate, and evolve, the very fabric of the cosmos becomes a vast, interconnected network of realities, each contributing to the greater whole. In this ever-changing landscape, the multiverse moves toward greater complexity, constantly shaping and reshaping itself, an ongoing cosmic dance of creation and evolution.